Tiger Beetle Sessions, Thursday, 16th of December, Session 5. Hey Joran, what's up?
Hey Isaac, great to be back. Uh, Pretty nice vacation vibe here at the office. Got the whole place to myself. Awesome weather here. So yeah, this is a great way to end off the year. This is going to be our last session, right? For
Indeed, last
2021.
session of the year. See you guys back in January sometime.
Yeah, yeah, I can't wait. Yeah. Hey, good morning, Nipsey.
You want to recap what we've done yesterday?
Yeah, yeah. So yesterday we were thinking we would start the day looking at level DB, and then we would do like just a generic B plus tree implementation. B plus tree where you've got all the sorted keys in the base of the tree. The key values all sorted in the base of the tree, and then above that you've got indexing internal nodes, which is just keys, and you've got multiple keys per node. Just a generic B plus tree. This is again, we're working on the LSM manifest. So the manifest is a way to keep track of all the metadata about tables in the LSM tree. So each tree has its own manifest, and each level in the tree has its own manifest. And the trick, what the manifest really needs to nail and solve well is the question of given a key, which is the latest table in the tree that possibly could contain that tree. So the manifest is keeping track of all the tables. There's about 2 million of them at most when we're addressing up to 100 terabytes of storage, which is pretty big. That's kind of like the scaling limit. And the manifest for each table keeps track of the minimum key in the table and the maximum key. And that's where we would be using the B plus tree to answer the question. Here's a key. Let's find the table info or the metadata about a table where this table could contain the key. So that's where we started in the morning. We're thinking we're going to do a generic B plus tree. Then we had some ideas around how do we make this concrete? What is our tree going to look like? What's going to be the shape of the tree? What's the tree height going to be? Because obviously the height of a tree is important because the flatter the tree, the better for read queries because there's less nodes to jump to for cache misses. So it's faster. And also because in the LSM tree, the tree has got already, it's like a pyramid with 6 different levels. So we're going to have one of these manifest trees per level. So it's kind of a multiplying factor. The manifest for the level has a B plus tree, which could have a tree of like height of 3, and then you've got 6 levels. So if you want to do a read query for a user, you're looking at 18 cache misses. So whereas if the B plus tree has like 10 levels in the height, then suddenly we're up to 60 cache misses, which is quite a lot. So that's why we were just looking at the shape of the B plus tree. And then we started seeing, oh, for our use case, we only have 2 million tables in the worst case. So we can actually, we know we only need a B plus tree of height 3, root node, internal index nodes, and then the base layer of data. And then we started realizing yesterday also interesting pathological case where if we're inserting transfers in increasing order of timestamp, if I understand correctly, our B plus tree is going to look pretty pathological. It's just going to be a ramp from the node with a huge amount of height, uh, which wouldn't be great. So then we started thinking, well, let's do something that is a B plus tree in terms of how the nodes look, but we're going to fix it. We're going to put it into like a
Mm.
straitjacket so that we shard the indexes across the nodes, and we're going to do like a bulk fill from the bottom up rather than top down. So we bulk fill the data in the bottom and then just incrementally recompute the index nodes that changed and the root node. That's where we were at. And is that it? Have I left anything out, Isaac?
I think that's about it, yeah. And I think the design we brought at the end would actually will work. It meets all our requirements, I'm pretty sure.
Yeah,
And so now it's just a question of like either implementing that one or if we can think of something even better, that would then give us advantages either in simplicity or performance.
exactly.
Um,
Yeah, because there's a little bit of, it's not too bad the implementation for this, but we've got a little bit of work to do with doing the indexes incrementally, or it's fine. It's all pretty good and it
I think
works.
it's not terribly complex, really. I think it's pretty doable what we've
Yeah,
arrived at so far.
yeah,
But I think you have got another idea now to pitch to see how that
yeah,
works out.
yeah.
Um,
So just to comment, like before we get to that, what's been pretty nice, like these last few sessions, is sometimes we ask these like outrageous what if ideas. Like what if the speed of light was 10 times faster? Like what would it look like? Would it be a good thing? We're not even asking like would it be a good thing? We're just saying what if we could do this? And then we see can we make it possible? Like could it even work? How could we make it work? Let's try and make it work. And then only once we've asked those questions, then only do we try and evaluate it. And we say, well, what are the pros? What are the cons? So it's like here's this way out idea. It's pretty crazy. Could we make it work? How could we make it work? And then how would we evaluate it? Which is pretty interesting. Like you get to some we've we yeah, I think we've done that quite a lot, like the last few months. So this is another one of those. So basically, we were at our Tiger Beetle sync yesterday with everybody on the team, and Isaac and I were sharing like what we're thinking. And DJ was saying, "Hey guys, what about just making the nodes of your segmented array much bigger and doing a binary search on that? Like what would the costs be?" So I was playing around with that yesterday afternoon, and but not doing quite that. So here's what I thought. I don't know if we can jump back to that spreadsheet, Isaac. If you,
sure,
uh,
I'll share my screen.
yeah,
Or you got pulled up actually.
okay, yeah, great. I must get there too. I'm gonna quickly get there on my side. So the yesterday LSM Manifest. Yeah, there we go.
Cool.
Cool. I'm in the house also. Okay, so here, just quickly getting my numbers that I worked out. So the other thing that was interesting yesterday was on Monday and Tuesday, we hadn't really played with the node size. We had always just assumed a node size of 4 kilobytes. And these are the nodes that we get from our static allocation pool, which means that all the different LSM trees, the forest has a single central pool that we statically allocate up front. And then as the trees grow, they steal from this pool. And that solves the whole problem of, we've got 30 trees, but we don't know who's going to be the biggest. But we do know that like our total addressable storage is N, and from that we can derive what the minimum should be of static allocation. And now the trees just steal from that pool. So instead of having to do a pool for each tree, which would be 30 times more expensive. But yeah, so yesterday yesterday was the first time we started playing with tweaking the node size, which made the 3-level B plus tree possible. So DJ's idea was kind of taking this further. So we make the node size even bigger. So here, um, I'm going to just work on the bottom here. If we do like this, node
Okay.
size, and let's make this 256 kilobytes. Um, key size, let's make it 8. Um, then let's say this is going to be our data layer at the bottom. So just like the B plus tree, we're still going to keep that bottom layer. This is
Okay.
this is the segmented array. So the other trick that I realized yesterday is we know our problem space pretty well now because we've explored what we needed to do. So I think if I understand correctly, Isaac, the only reason we need the B plus tree is to, given a key, find the table info that intersects it. And then
Right?
once we've got that, the second thing we need from the B plus tree is to do fast iteration across subsequent
Right.
sorted table infos. So I
Yep.
realized what we want to do is, I think we've been thinking this all along anyway, but our B plus tree is only containing keys,
Yep.
because that means there's less baggage coming along to bloat the cache misses. So if our node size is 256 times 1024, if our key size is 8, let's move this along quick. And if we've got tables max 2 million equals 2 times 1224, then node size. Now we've got key size like that, so we can do keys per node is this divided by this. Now we need to know how many nodes do we need. Nodes count equals this divided by this. So we need 64 nodes. And that's
Well,
interesting.
hold on.
Yeah.
Like, where are the values then?
Uh, so what I thought for this idea is we solve we solve the problem separately. So we need the keys to be in one B plus tree for solving that first problem. And we'll get to the values, the rest of the data, because the rest of the data we actually only ever access when we iterate. Is that right?
Yes, but it's like getting then you want to be able to put in O1 time from a key to a value. So it seems
Yeah,
like the problems are very tightly related.
yeah. No, we'll get there. So once we get the key, we need to get the corresponding info as well. But most of the, like when you're looking up keys, you're doing quite a lot of binary search hops there. Then you find the key,
Right?
and then you get to the table info. But we can tweak this either way. This is not, it's not essential, but I think this might make sense. Let's see how we can evaluate it later. I'll show you
Okay.
the overall structure, and then we can tweak it from there.
Sure.
Okay, so the trick with this is that nodes count is 64, which is like a special number, because what you see, all we've got now is just a segmented array. We've got 64 nodes. Each node has
Yep.
32,000 keys. If we were to do a binary search just on this, we've got to do iteration each time, but we've only got to do iteration of 64. So it's not bad, but it's not great. We probably don't want to do that, I don't think. So
Yeah.
here's how we get rid of, so this is the problem we want to solve is, given a key, locate the first table info, like do like a range query, on this data. So it's a binary search on the keys. And as we're doing this binary search on keys, we want to minimize having to also iterate on the segmented array. So let's solve that problem. We get rid of all that iterating across the segmented array as we do the binary search for the key lookup. Now we do a little accelerator on these nodes, which is just keys in sorted order, binary search. And this is going to be 64 nodes times the key size, which is 512. And this accelerator is pretty special because what's interesting with this number, uh, how many cache lines are in here? 8.
8.
Yeah. And
Yep.
Isaac and I were chatting about this just before we went on stream. There's something new we've kind of learned as DJ was working on the block preset compression stuff we're doing for the super block for all of this work. We realized that if we're going to do a cache miss to load a 64 byte line, what happens is like the memory subsystem has spatial locality. So if you do the cache miss, you pay the cost of it. The memory subsystem can prefetch, and the little line fill buffer on each CPU core on like Intel that can do 10 cache lines in parallel. So we're doing this is our reasoning. I mean, it's pretty, there's a lot of stuff under the hood, but our overall intuition is that we do the cache miss, but actually the neighboring lines, if the CPU is going to be doing prefetching, then it can already fetch 10 in parallel. So, we were designing some other structures where we were thinking, okay, everything must only be 64 bytes, but it actually makes sense to amortize the cache miss a little bit because you actually get the neighboring lines free. So in some of the new papers lately, they call this the effective cache line size being greater than 64 bytes. It's actually either 4 or 8 or more than. So for example, Apple M1 chips, they can fetch more than 10 lines in parallel. So they would have a much higher effective cache line. That's why they're so fast, because the memory
Yep.
subsystem is just the normal, like on Intel, the per core memory bandwidth is like 6 gigabytes a second. On M1, it's like 24 gigabytes a second. So it just ready, and most software is actually not CPU bound, it's just memory bound. Uh, Memory is like the new spinning Rust. Uh,
Yeah,
so anyway, so I thought
pretty much.
this accelerator is just keys, it's just sorted keys of the nodes, but it's pretty nice because it's actually the ideal size. Um,
Yeah, that's basically just the root node,
yeah, just
or
one
the
root node.
index,
Yeah,
or just we could just call it the index, I think.
yeah,
Yeah,
exactly.
and
Or
this works out. So then for 32 byte keys, this is just 4 times as big, right?
yeah,
Or
it's
is that
just
more than 4 times as big?
it's a little bit
Um,
bigger, but that's fine. Uh,
yeah, oh yeah, it's what it looks like 16 times as big.
yeah,
Four
yeah,
times 4 times as big. So you get a four squared in there.
exactly, because
Um,
the keys per node decreases. But
yep.
this is only for a mega cluster at max capacity, and our binary search on the root node accelerator or the index node, that only does the binary search for as much as is in there. So we
Yeah,
wouldn't,
yeah.
yeah,
I'm not worried about that being slower. I'm just
yeah,
thinking of how we do static allocation. But I think we just like statically allocate for each tree individually, then the index,
exactly.
and that's just done in initialization, and that's not that much memory really. That's only,
No,
yeah, what, 8
so
kilobytes?
Exactly.
Crazy.
So I worked out all the static allocation overhead for this whole scheme, and the good news is it's fine on everything. Uh,
Nice.
we can plug in
This,
these numbers, but actually we can even statically allocate all the pointers contiguously for the data nodes, so that we
oh,
can O1 index. Once we've located the key, we can O1 index to the related rest of the table info.
well, yeah, that just like saves us storing the pointers in the accelerator itself. We need to
Uh,
store them somewhere, but I think that's the right way to do this. Is like
Yeah,
you store list of pointers, list of keys in the index. So then the accelerator memory is also actually then times um or we need to add then the pointers to the accelerator memory total,
uh, we don't
essentially.
we don't need to, because we can actually the underlying keys in the segmented array, those pointers are also statically allocated, and we can,
Yeah, that's what I'm
yeah,
saying is that that's part of the accelerator or the index allocation is what,
yeah,
at least
yeah,
that's
yeah, yeah, yeah.
how I'm thinking about it.
The
Um,
total static allocation cost. Uh,
yeah,
so
it's
yeah, sorry,
the
I
256
misunderstood.
pointers plus
Yeah,
plus
yeah,
the plus the 256 keys.
yeah. So I worked out the numbers. It's basically um, the static allocation is going to be 5 megs for the accelerator for the little the overall binary search across the whole
Yep.
forest. So everything here is across the whole forest.
Wow.
Uh, so five megs for that, which is fine. Because to put this in perspective
Yep.
again, like for our forest, we're already doing 140 megs, or I can't remember, 120 megs just for our mutable tables. So this is
Right.
five megs. Then the static allocation for the separate keys, because we've taken those out of the table info, that's 11 megs. The rest of the table, we also get better alignment like that without padding. So that's 11 megs. For the rest of the table info, it's another 11 megs. And then the static
And how do we do
allocation,
that?
the rest of the table info.
Yeah.
So the rest of the table info is just another segmented array, uh, and that's it. And the indexes correspond one for one with the. So we've
Okay.
got two segmented arrays.
It seems like it'd be simpler in some ways to and so the indexes correspond one for one. Doesn't the node size have to be bigger then because the table infos are bigger?
Um, we could. That's the other advantage is we could make the node size bigger here. It's actually better if we make the node size smaller for these because we pay less static allocation overhead.
Okay,
Uh,
but so the index, so we're doing indexing into a segmented array again then, right? We just
yeah,
owe like nk or whatever, or k and log n.
yeah,
Um,
yeah, yeah. But we should actually just put the table info all together. We don't need to keep the keys
I
in the
think
segmented
I
array
think we should do what we were doing
separate.
before and just do structure arrays in each node of the segmented array, and maybe then make the node size even bigger. So I think our upper bound on the node size is determined by how expensive it is to split nodes and do m copy half the node. Is that right?
Mm, Not that that's not really a problem at all, like for any of these node sizes.
Okay.
It's the bigger problem is that if we do structive arrays on everything, we pay more and more static allocation cost because we have to do one node for each field, we have to do a whole node as if that node only has one element in it. So we have to do the static allocation
That's not what
when
I'm really proposing.
no.
Um,
I'm just explaining something
but yeah,
separate. Just to some. This is what I
I
was
agree with you
working.
there then. Yeah.
Yeah. So
Cool.
what we when we think of the structive arrays, the trick is that we should only separate out from the table info what we really need for the key lookup. The other stuff, it's better, it's cheaper for static allocation to group that together because we pay, what I worked out is, so if we do structive arrays just for keys, that's 11 meg static allocation because we have to statically allocate the nodes as if the nodes are all at least half full. Plus, for every tree and for every level and for every other field that we do this, we have to pay the node size as the overhead. So if our node size is like 256 kilobytes, then it looks at like it's basically 44 megs per field that we do structive arrays on. So that's why it's actually better to do only the key as structive, store the key out of band because we use that for the binary search on keys. There we pay like if we use, for example, a node size of 64 kilobytes, which is a little bit better actually than the 256 that I've showed us here. So 64 kilobyte node size, the static allocation for the keys segmented array is 11 megs across the forest. Then the static allocation for the rest of the table info is also 11 megs because you
Why don't we
win.
just, yeah,
This
cool.
is the additional static allocation on top of what we would have to do for the pool allocator. This is where the one of the nodes only has one table info in it, but
Yeah,
you
yeah,
still you so that
right.
bit
I'm,
becomes cheaper.
I'm with you there.
Yeah.
I'm just wondering why we even put the table infos in a separate segmented array. What's the advantage there?
I'm also thinking about that. So maybe we just put it all in one and don't do structive arrays. Just do one
I think we should
seg
just put it all in one. Or we
one
do structured
segmented
arrays
array.
internally to the node is what we do, like we have in our current data layout. Like we're
Yeah.
already doing that in our current
Uh,
like
okay, of course.
this
Sorry,
is what I
Isaac.
was proposing.
Okay.
This.
Okay, cool. Sorry, I misunderstood. I was referring, we were talking past. I was thinking of structured arrays in terms
Yeah.
of segmented arrays, multiple segmented arrays. Uh,
I realized that at some point, but you were already on a roll. So,
okay.
but yeah.
Okay, well
Anyhow,
that's
I think that.
Yeah.
We just need to make the node size bigger to accommodate enough space for that then, so we can still have only
Yeah.
36 nodes. But that means making this quite large. I'm not sure. The table info size then becomes 104. That's then about 3 times as large. So I think we're gonna have to make the accelerator also 3 times as large again. But maybe that's still fine.
Yeah.
Do we want to run the numbers on that?
Yeah, let's plug it all in and work it out. Because I realized,
Okay.
the accelerator, it's variable length, so we'll do the binary search on as much as is there. So it actually works really nicely for, you know, for typical cluster versus mega cluster. We'll get
Yeah,
great
I think that
performance.
the accelerator. I think this idea will be faster than what we had before. It's also simpler to implement, so I like that one too.
Exactly.
Um,
Super simple, eh? Thanks, DJ.
oh yeah.
DJ was like, "Hey guys, why didn't you just do this?" Uh,
Well, I mean, he didn't have the accelerator part. He was just like, say, what's the
yeah,
advantage over doing just the straight indexing into the segmented array,
yeah,
which is a bit slower than the B tree because, or the not, it's not even the B tree. It's like our weird thing where we have 2 levels of indexes.
yeah, yeah,
Um, but we didn't
yeah,
consider making the node size really, really big yet, I guess.
yeah,
And so we get some overhead there of memory, but I think it might actually be less in total because then we don't have as many index nodes. Um,
yeah.
anyhow, table
And
info size is going to be, what do we do here? So 16 plus 8 plus 8 plus C5 times 2. I can just copy this.
and you're yeah. Sorry that I was on a roll back there. Thanks that I
All
could.
good.
Uh, the your idea of just putting it all in one segmented array, because internally those nodes are doing struct arrays. That's just way better. Uh, so much better.
Yeah, it's a lot simpler. Then you don't need to do any segmented array indexing, which is what I've been wanting to avoid this whole time.
Yeah.
Why is this yellow?
I
There
don't
we go. I
know.
fixed it.
Okay. I'm
I
gonna
don't know
come.
how it became yellow, but
I,
it's
don't-
not yellow anymore. That seems wrong though. I think I missed an 8. Yeah, there should be 3 8s in there.
hmm,
So there's the other timestamp as well.
deleted. Yeah.
All right. We can like fill these things down now, or can you like fill them all down at once?
You can. Yeah. Just like that.
Nice. And now maybe like do some more key sizes.
Hmm. And this is like super simple, yeah, Isaac. Like just so
Oh
simple.
yeah,
Like,
this will be so nice to implement. We'll get
yeah.
this done today. I hope if we start doing it in the next
Yeah.
like 20 minutes.
Exactly. That's what I was hoping. Yeah. I was wondering. Yeah. I thought, hey, we could even finish this.
Yeah. So how are we at now? So now we've got keys per node. We still got 32,000 keys per node with size 8. Nodes count is still 64. Oh, we haven't changed this formula yet. I see. Are you doing that now?
No, not yet. Which one?
Okay,
Keys per
I'll fix
node.
it then.
Okay, you go for it.
It's not, we're still using size instead of table info size. That's the problem.
Yeah.
Um, now it's gonna work out a little bit less nicely. But I think what we do is we just make the node size even bigger. Um,
So
um,
the one separating the keys out of the table info, that helps because it decreases the number of nodes. And
well,
then,
we can just make node size bigger. We can make it two megabytes.
yeah,
Um, and then we're down to 56 nodes.
yeah,
It's just to play around with the numbers, but
yeah,
I think
that's
node size isn't really. So what's the point where memcopy starts becoming an issue? Is memcopying like a megabyte still fine?
it's all
Um,
fine. Yeah, no problem. The the problem with getting to larger node sizes is that we pay that static allocation cost for the plus one node,
right, yeah,
where
that's right. So you get memory overhead, but maybe that's
every
fine.
level
I don't know.
I'll work it out for us.
Sure. can we add that just like as a column in the spreadsheet?
Good. Much better. Does that make sense? The +1?
Yeah, the +1. I understand the +1. I'm
Okay.
not sure the exact formula to use there, though. I think you've got a better handle on it than I do currently.
Yeah. It's just the size of the node times the number of levels times the number of trees.
All right, cool. Size of the node times the level of number of levels and times the number of trees. And so each level needs at least one node.
Yeah.
And so we have a potentially nearly entirely empty node there for overhead.
And that costs 360 megabytes.
Really?
Yeah.
Okay, yeah.
And I think that was why we didn't consider this idea earlier.
Yeah.
Also because we were thinking of iterations still over the segmented array with smaller nodes, so you've also got more iteration. But my thinking is that if we can locate the key and do that very quickly, and then we've got a O1 jump to the rest of the table info, which can then store the key as well, because that way iteration, we don't have to jump back to get the key. The table we basically just duplicate the key.
Yeah. I don't see a way I think that's what this is doing. The tree structure, you know?
Yeah, but check this out. If we split it out like this, our static allocation gets very good. That's kind of what we're looking at, and that solves it for tables
Wait,
max.
hold up. Why is the stack allocation for the rest of the table 64 times 1024 times 6 times 30?
So this is the +1 empty node. So this is
You see,
where so
okay,
you see,
so but you're saying the table info uses the same node size, essentially.
exactly, and
Okay.
the
And
+1 cost
there's no way
is
to index though. There's no way
the
to go from key to table info in O1 then.
there is because the pointers for all of these segmented arrays are also contiguously allocated, and I've the cost of those
Okay,
pointers
but you
I've
don't know which segmented array the table info is in,
it
do you?
they're one for one with the keys. We basically this idea we've got a
Well, that doesn't work though,
segmented
because the
array.
table infos are bigger.
You mean
You
the
can't fit
static?
as many of them in a node as you can in the keys.
So let me explain.
Okay.
This static allocation, it's independent of the size of the table info. The way you work this out, this +1 empty node, this is basically that's what these two 11 meg numbers are.
Yeah, it's only based on node size. I see that. I'm not seeing how
Yeah,
you get from the keys stack segmented array to the table info stack
yeah,
segmented array in
yeah.
O1.
Okay, so here we've got segmented array of keys, um, segmented array of values, and these indexes correspond one for one. You can just use a function because of you can take the ratio of the key size to the table info size to work out where you can go straight one for one between the two.
I'm not sure you can, because the nodes will get split at different times because the size is different of the keys and table
Y-
nodes.
Yeah, yeah. So I don't mean that. So I don't mean that they're in the same node, but you would then iterate across the bottom values. Um,
Okay, so it is O over the number of nodes then.
Yeah, yeah, but we're also going for bigger nodes, not 2 megs, but we're going for bigger nodes so that we've only got a. So basically, you do the binary. I'm not saying we should do this. I'm just saying this is how it could work. So we do the binary search very fast. We find the key. Now we know the logical index of the rest of the table info.
Right. And
Um,
yeah.
the rest of the table info, we go into that segmented array. We have to jump, but we can hop pretty fast because we're storing the counts also. So we can iterate. You know,
Okay.
it's at most 64 nodes. Then we get to the but once we're there, our iteration from there on is super fast. because
Right.
we only iterate
But
table
yeah,
infos, and that's all
that's not
continuous.
constant time though, which is why I was confused. Because you were saying it was constant time, but it's not constant time.
Yeah,
Um,
to me, I'm thinking of the it's like O1 plus the constant for the segmented array iteration, those 64.
okay.
Yeah.
You just like use the okay. But also like knowing the key index of the key is also or it's the O of k, where if k is the number of key nodes. Otherwise, you don't know the index of the key.
No,
You have to
the
store the counts up,
uh,
and then you know
oh,
the index
oh,
of the key inside the array is in, but you need to also add the node counts in the previous arrays. Um,
yeah. Which purpose is that for, Isaac? What function is that?
well, you need to
Uh,
know that. Well, once you found a key in the keys segmented array, you need to find the index of that key. So that you need to know which index that key is, so you can then go look it up in the other array.
yeah. So I was
Finding the key
thinking,
doesn't actually tell you the index. It only tells you the index inside the segment you're in. You then need to
so
find out.
the
Yeah,
accelerator will have the keys, but it has the keys per node. So the accelerator can tell you
so it stores that count as well. Yeah,
it
but it's
tells
just
you,
another okay overhead. I'm sure I'm totally confident we can do it. It's
yeah,
not complex. It's just there's another like little constant overhead there.
yeah.
Um,
Let's go back. So are you happy that if you're looking for a key, we go into the root node, binary search, that'll tell us straight away the key node, and we can jump to that key node O1 without any other overhead because
yeah,
we're going straight to the key node.
that's totally cool with that. Yeah.
Yeah.
The
Okay.
problem is that you don't know what index that key is in the whole segmented array of keys.
Uh, we, we do. Uh,
You know
be,
the index in that specific block of the
key,
segmented array, and that's
e-
node.
exactly. So the
To
next
find the
step.
index in the whole segmented array, you need to add up the counts for the previous nodes. They might not be full.
Okay, cool. But that we can do like just separate contiguous also. Like that's not difficult. And we've got all the
Yeah, that's what I'm
counts.
saying. It's not
Yeah.
difficult.
No, no.
It's more overhead
Yeah,
to
yeah,
then
yeah.
go
Oh, okay.
from key segmented array to value segmented array.
Yeah.
Um,
I mean, we can even store that in the accelerator after the keys. We can store all the counts. So it's all
yeah,
together.
that's what we would do
Yeah.
too.
Yeah.
Essentially, we store another parallel array there of
Mm.
counts for each node,
But
and it's
that
also a little
doesn't
bit more stack allocation, but it's not too bad.
it doesn't
Um,
really affect the performance. Like it's going to be pretty fast.
well, it depends on how many nodes we have. Um,
But we
but
aren't
it would be
we
pretty fast. You're right.
like 64 nodes. It's not. Uh, so those counts would also be in one effective cache line. There's just two effective cache
Yeah,
lines.
it's just a bunch of
Uh,
U32s.
so we can find those
I should.
keys super fast. Once we get into a key node, we'll do a binary search to find the actual key. That gives us a logical index. Then
Yep.
we can traverse the segmented array of values, but we can skip over quickly because we've also got those counts. So we can pretty quickly get to an index. We
Yeah.
can even keep those
I think that's
counts in their own effective cache line. Uh,
that's pretty fast. I'm not sure those counts all fit in an effective clash line because you've got a lot more nodes for the segmented array of values than you do
mm,
for keys.
mm,
Um,
yeah, exactly.
how
Because
many
the
nodes do we have? I think the stack allocation gets pretty big if we want to do the same thing with an array of pointers. Um,
so I've worked that out over here. You can see here we've got more nodes because there's more data.
info node pointers.
Yeah.
Where does this 2304 come from?
Uh, we should probably rework this out, but this was based on 32 byte keys, I think. Yeah, it was. It was 32 byte keys. Uh, so we would need more nodes to store them because the table info is bigger. So I worked, that
Yep.
should be correct.
I expect it to be more like 3 times the number for key node pointers. table infos are about 3 times as large as the keys.
and that's what you see here. So 180 times 3 to get to 405. The
Okay, well, what's the
actuals.
2000 number though? That's what I'm confused about. 2304.
Uh,
Is it the
yeah,
number of nodes or something?
it's the number of nodes. Yeah.
Okay.
I should have, yeah, this was just rough, so, um,
Yeah.
but we should redo these here now in Excel.
Yeah. I'm still wondering if we can just make it work out with just only one segmented array because that'd be simpler.
Yeah, it would. The
It'd be a
disadvantage
bit
would,
more memory overhead, but it'd be faster and simpler, I think. If we
the,
take this down to like 1 MB, how does it look like then? Um, um, 180 megabytes stack allocation for this. It's
yeah,
not too great.
yeah,
Um,
and the disadvantage is that the accelerator now gets very big because there's more nodes.
yeah.
So what I think we should do is have two segmented arrays, the one just of keys, so we're solving the
Yep.
problem of getting that initial logical index. The second segmented array can actually have the whole table info, so that
Yep.
iteration doesn't have to
Yep.
go looking for.
I'm all with you there. I know.
Yeah,
I understand your idea for sure. I
yeah,
just want to know how much data these table info or we want to see how many nodes the table info array takes up for these
yeah,
different key sizes. I think is the next step.
yeah.
Um,
So
so
you're happy with the overall like two segmented arrays,
yeah,
accelerator. Yeah,
I just want to see
yeah.
how it works out with the numbers. I
Cool,
understand the idea for sure. It'd probably be
cool,
pretty good.
cool.
Um, and
Um,
but it depends on how many nodes we have in the table info array. If the indexing to there is going to be fast or not.
yeah,
Um, I'm gonna put this back to then being based off key size instead of
yeah,
table info size for keys per
yeah.
key node, I guess.
I'll do a separate column for the, um, maybe we can do it. We want to figure out how many key nodes there are and how many info nodes there are.
Exactly. This is gonna be key node count. Node count. So it's 1,792. And for well, we need to probably like make some more columns here to have like the total index static allocation overhead, or like the
Yeah,
total allocation for the index and the total allocation for the table
yeah.
node stuff.
We should have like there's two plus ones and then there's the pointers for each.
Yeah, so let's move the plus ones should be all the way at the end, but we need the pointers and counts if we want to make this fast.
Yeah,
Um, we have yeah, there we go, 2 columns. I'll do the key, the index overhead.
cool.
Um,
The plus ones are actually, it's just times two because it's the same for both, regardless of their size.
Yep.
So I'm just going to do one column.
Those can just be just one column maybe. I don't know.
Hmm,
Um,
that's what I'll do. Is that index pointer for allocation?
That's index. So this is the key keys, pointers, and counts for each node. So this is for each node you have a key, a 8-byte pointer, and a 4-byte count.
Okay. But
Then we need the same thing.
okay. We can, I was thinking the key nodes are going to come from our pool as well. We'll have, it's all the same node size, so we can steal from there and we just do our min half full.
Sorry, what?
We,
Is that related to what I just said, or is that something else?
I thought I'll just tell you so you could work it out if it is related. I'm not sure.
Okay.
Um, I'm just adding it as an extra data point. I don't
Okay,
know,
cool.
should we show the pointers separately, like the contiguous static allocation of key node
Well,
pointers?
we've already got we've got the index with just the keys here. Then that's 2048, and we've got here
Yeah,
the total index size, which is then the um the index plus the pointers plus the length. So this is like the total overhead of the total static allocation needed for the index for each level of each
plus
LSM tree.
okay, plus the key node pointers. Yeah.
This is the keys plus the pointers plus the counts for each node.
Okay, cool.
Um,
And then we must do that times 6 times 30.
well,
Um,
we also need to do this for the table infos, which is going to be bigger. So I need one more column here, I guess. I was going to
okay.
take this column here.
What? Maybe
Um,
shall we show these just per tree or just per level, and then at
these
the
are per
end,
level. At least this one's per level. Um,
exactly. And then at the end, we'll keep these all per level. At the end, we'll add them up times levels
yep,
times by trees.
that sounds good. Yeah.
Okay. Then
Yeah. So then for the plus one, we should make that per level. You're right. That makes sense.
cool.
Keys. This is gonna be count. Okay. These are all in bytes.
Yeah, same. That's right. So what I've done, uh, index total bytes, node per level alloc, and plus one, they're all in bytes. Then forest
Yep.
is in megabytes, and
All
that's
right.
yeah,
That seems to work out. 40 megabytes is okay. Well, that's the
yeah,
overhead. And we also need the memory for the pool itself. What is that then? Um, we need the memory of the nodes. So then it's 11 megabytes. This is the static allocation. We also need like to see how many nodes we would need for a full forest of this many
exactly,
tables. Then we can add
exactly,
those two things together to get the total memory required for the manifest.
exactly.
This is really what we
Well,
should be caring.
and that, but that pool allocation, we almost don't have to worry because that's optimal, and we can do nothing like that. That's the same no matter what approach we do. Uh,
It's actually more with this approach because we have separate key nodes.
Yeah. But we've accounted for
Before,
that because those key nodes we put into this cost. Uh,
what?
we should put the key nodes into this cost. Oh no, we shouldn't. No, it's coming. It is more like you say. So we need to
Yeah.
work that out. But there is not going to be much more because the
Yeah, I
keys.
think it's gonna be. I think it'll be totally fine. I think you're right
Yeah,
that it's not a
yeah,
problem really. It's
yeah,
just like, yeah. So do you think this is like this numbers work out? Is
yeah,
this like good enough to roll with it?
yeah. I'm happy.
Um,
We
th-
we're going to inflate these numbers a little bit because we're not taking into account here that the segmented array nodes will be at least half full. We haven't what we've paid the
oh,
plus one cost, and then we just need to
yeah,
pay the plus one cost is the most heavy, and then then
yeah.
there's the half full, which affects
There's
these
also
two.
this thing that might be a showstopper. We've got to iterate now 3,000 U32s and add them together to find which um table info corresponds to a key potentially, like in the worst case. You
Yeah,
see this column info node count. We've got to iterate over all these info nodes. Oops, that's not what I
yeah,
want to do.
yeah,
To find like, which key corresponds, or the input of the input corresponds to our key.
yeah.
And we've done this.
We could solve that, Isaac. Or what we can do is our accelerator. We've got the accelerator has the key min for each key node. We could also add to that the actual index node index of the index node that corresponds to that key min. So that if you've used the accelerator to get to a key, you can actually jump straight to the info node.
I don't know if you can do that. I
But you,
think
you you can basically speed up your iteration by starting much
I don't
further
know
along.
how you can maintain that data.
Okay. Can we find a way to do it that we can, because you see at compaction time, we can basically add little helpers that say, I'm just saying if we could make it possible, uh, some strategy like where we at compaction time we do extra work so that if you have found a key node, then the index node for that will be at, because remember we only ever mutate this during compaction and then it stays immutable. So we could pre-calculate for each key node,
Okay.
at least for the key min of the key node, we could say here's the corresponding index node, because that way you know if you
Well,
found a if you found a
this is the
key node,
thing.
if you found a key node, the actual key you're interested is somewhere further along, but you do know that your minimum info node index is this, so you can already start your iteration much further ahead, and then
You
just do
actually
the.
can't do that though, because to get to that index, you need to iterate the first all the info nodes up to that point, because you don't know absolute indexes. There's no way to index absolutely with O1. You always have to start at the beginning and add up the count for each node in the segmented array to get to that index. Then you know which info node you're on at that index, and you can keep going from there.
Yeah, but if we have a segmented or if we have contiguously allocated not only the info nodes, we can also even for that info node we can also do all pre-computation during compaction. Like let me show you.
What are you pre-computing? I'm confused about this. Um,
So let me show you. I'm gonna put it in the. But this is what we would
okay.
pre-compute. Cool. These are all info nodes. These are in our. These are all like 64 kilobyte node sizes, right? These pointers are all statically allocated that we know. For each of these, we can already say cumulative count. It's not, and so what we can also say is in our accelerator, um, I mean, we can actually do a whole lot of stuff to make iteration very fast. Um, here's a
I'm
key.
not seeing what that is, but yeah,
Do you understand this one? Cumulative count.
that's what we already have in this indefinite node for level alloc thing, I believe. We have
No.
here a count for each node in the info node according to the list.
Yeah, so cumulative count is different. Cumulative count
What is that
is
then?
it's the sum of info node counts across the previous info nodes. So if you've got an index to an info node, we can jump into this straight away, O1. We can jump into this O1 as well to get the cumulative count up to this info node. So here there's info nodes that went before. We don't have to iterate this anymore because we've got an index to a key node. That can also give us, we can be tracking extra info to get straight to the info node that corresponds with the key node. So we only have to start our info node iteration here. We can already ignore a huge chunk. Um, do you understand the cumulative count? It's the
The
count of
cumulative count is
counts.
the nodes before the current info node you're looking at.
Yeah,
And so the first thing you do is you iterate. So I'm just like thinking about the lookup algorithm. So you iterate the index. So you iterate over potentially 1,000 index keynode counts to find the index in the keynode index. Then you've got um, well, where does this index to an info node come from? How do you know which index to an info node you should be using for this keynode index?
uh, so the keynote tells you when you find a
How?
keynote,
Or
it's pre-computed. So the keynote has its own key min. It's the minimum key in that keynote.
right?
When we create this at compaction, we do basically just a linear scan over everything once, pre-computing these, and the for this, so the keynote has got a key min. We add an extra field that says here is the index into the info node that contains this key min. So you
I feel like at that point you might as well just like start pointer. I don't know. Or maybe okay, index is fine. Into the index into the slice of infinite pointers is what you mean. Um,
exactly, and because the index is cheaper than a pointer, and then you've got this cumulative
okay,
count
but
also,
that
so
doesn't
you
work
can
though because you need to split these indexes in a slice won't be sorted is the thing. Is they need to be split and or do we just like mem copy the rest of the following pointers in the slice? Is that what we do?
I,
Um,
I don't understand, Isaac. What is not
so
sorted?
you've got this slice of this is maybe fine. We've got I guess a slice of 3,000 info node pointers. Um, and we want to then split like the first one in the slice. We just
Yeah.
mem copy the rest of them to make space then. We can keep it sorted.
Um, so these cumulative counts and things, we don't need to look at. I'm thinking of this all as like bulk load. So at compaction time, we'll modify our raw,
Yeah, I've seen that. Yeah,
yeah, and
me
then
too.
right at the end, we'll do a single pass over all of the info nodes and keynotes to relate them to each other to update the cumulative counts and indexes.
Okay, yeah.
So it doesn't really matter then that they stay in sync while we're doing individual inserts. Right at the end, we just go over. But also because our like for example for the keynotes, we've only got 64 of them. Constructing the accelerator is very cheap. It's super cheap to do that. Info nodes, we've got a few more, 2,000, 3,000, but that's not that bad because we're only doing it's yeah, this is something we do once at the end of compaction. So we'll modify our whole thing, put in tables, and then we'll do one loop over. to update our indexes. Have I understood
It's just starting
correctly?
to feel more complex than the other approach.
No, no, it's way simpler. I mean, we've got a super simple accelerator for binary search, jump to the key, and just a way to pick up your iteration in info nodes without starting from the beginning because of cumulative count. It's one number.
And so and the and then
And
every time we insert, we have to iterate the whole. It makes inserts really slow, but maybe that's fine.
no, 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 not. It's not every time we insert. We do multiple inserts. At the end of the
That's not every time we
inserts,
insert. Like
it
any
isn't.
insert could make the cumulative counts change.
Exactly. It isn't every time we insert. We in compaction we insert multiple times. After we've done that, we insert multiple tables synchronously. Um, Once that's done, we rebuild our accelerator. So it actually makes it much simpler because we don't have to worry about keeping indexes incrementally up to date, which is very tricky. Like in our old approach, that it's quite scary what we have to get right to make that work. This, we amortize across our inserts. We're doing multiple inserts during compaction. Right at the end of compaction, we have just like a simple index function that constructs our accelerator and our cumulative counts, and we're done. And we do that literally, we brute force it. We don't have to do that
Okay, so during
increment.
compaction, we just like keep track of all the tables we want to insert, and then when compaction ends, like in a separate buffer, we just like store table infos temporarily.
And
Um,
which we have to do.
and
And
we say that then we've got a method to like insert a batch of tables and rebuild the index.
exactly, that's it. And the rebuild is super fast. It's pretty cheap.
I think it's not terribly slow. It's not like crazy fast.
No, it's pretty simple, and it's going to be within our budget, and it's
Okay, so
safe.
we need to update the calc a bit here because we don't have these things included up here.
Yeah,
So index to an info node. I'm still flaky on this one. That we just have to store that as well. So it's another. This is then an index to the first info node that could correspond to this key node. So each key
it
node will
it
correspond to many info nodes, but it won't be a fixed number. It will be a
it's
variable number.
yeah. Let me improve so it's index
Well,
to an
isn't there also like overlap between these things? I think that is the case, but maybe it probably doesn't matter because we can just include them twice then. Um,
that's it there.
so this
So
keyring won't be on the info node boundaries, is what I'm saying. So it'll be in the middle of some info node. You just use that info node, but the first one's possible to find the key min.
yeah, exactly.
Um,
Then when
and
you
then
sorry, over to you.
then we so this is something we pre-compute. And to do that, we've got to iterate. Well, I guess we iterate over just the info nodes and the index is what we do, and the index keys.
Yeah,
Um, in each info node, we kind of look at the first and last entry to see the min and max key of the index node, of the info node, and then see if the first key, we can even just look at the first key of each info node to compare with the key min, and then take the first info node that matches.
yeah,
Um, um,
exactly.
and store that. Then we store that index. We store that index in our index total bytes. So I need to add one more U4 or U32 here, I
Yeah,
believe. So that's an index. And so to go from keynode to index of a keynode, we're still just going to iterate this info node count numbers every time, or no, this index node count numbers every time. Is that correct?
uh,
Um,
no, we can actually start the iteration in info nodes pretty close to where the key is.
Sorry, what? No, I'm talking about the keynote index. Um, but maybe we don't need this at all anymore. We just need to store this one number parallel to each key. I think that's how this works. So we actually still have just one U32 here. That works out.
Can
We
you
don't
explain?
store. So
Okay.
before I had here the count of the keys in each key node, but we don't
Yeah.
actually need that anymore
No.
because we've now just directly cached the count, the count number, the index into this slice of info node pointers that we need to use for this key min in the key index.
Yeah. Yeah.
Um,
Yeah.
we're actually or fine there. So now we've got
Okay.
that one. And so now we know the info node to start looking at. Then we go to that. Um, we still don't know the exact info node index though, do we? Um, I'm still
No,
clear. I'm
we
not clear on that then.
definitely not. Yeah, we don't have the exact info node index. What we do have is we know the key node that the key was found in. So here's the key
Right?
node, and the key is somewhere in this key node.
Yep.
But for this key node, it has a key min, and for this key min, we've pre-computed the index of the info node we'll find it in.
Right.
So because it's all sorted, we jump to the info node, we start iterating there, and we know that we're then going to eventually hit the info node that we're exactly looking for. But what the
Okay. So
point,
we
the
are still doing
point,
a bit of iteration,
a little
but
bit of iteration, but we're not starting from the beginning. So
yeah, that's probably fine. We don't need this
that's
cumulative count stuff then. This stuff can all go. All we need is this single index to the infinite that contains the first key min and the key node. We don't actually care about the absolute index of the info node anymore. We just
but
jump to this first info node that might contain the key min and iterate from there.
but I think we need the
So we don't.
cumulative count because when we iterate, we need to know how many info nodes went before in the half full info nodes.
Why though?
Because we need to keep track of the index as we iterate info nodes,
Why do we need to keep track of it? Like, what do we need the index for?
because we've got to get to the index that we found in our accelerator for the exact key.
We don't know the index in the info node though. We're just looking for the matching key. Man, that might be the problem with this. There's no way to map from indexes in key nodes. Or well,
There,
I guess we do need
this
that other stuff then. Okay,
this
yeah, I
is the
see.
way
So
this
like
is
we
the
can't
way
get
to
rid
do
of this
it.
U4 then. So we do need to iterate. We do need to find the key index,
Yeah.
and then we just like parallel indexes then. Okay.
That's why we need the cumulative count. So the accelerator
Yep.
helps us get
Um.
to the keynote,
Yep.
and then the keynote
I'm
helps
with
us
you
get to
now.
then we know the logical index of the table info we're looking for. We know the
Yep.
logical index we need to iterate to find. Now we want to speed up the iteration in the info nodes. So, but we're looking for a logical index in there. We don't know how much stuff was in the previous info nodes that went before, so we pre-compute the cumulative counts. Now we can pick up the iteration, start just before,
Exactly.
and the iteration's
And we
not
do the
gonna.
same thing for the. We can do the same thing for the key nodes actually. We can do cumulative counts there too instead of Yeah.
Exactly, yeah. Cool.
Cool. I think I'm up to speed with you now here. I agree this is going to be pretty fast.
Okay.
Or at least fast enough.
I
Um,
I feel a bit more comfortable that it's simpler also because just rebuilding the index is a lot simpler than incrementally getting it right, like what we were doing yesterday, you know? Uh,
oh no, I think that's also pretty simple to be honest.
okay,
Um,
okay. But this,
I definitely like understood yesterday's a lot faster than I just understood this.
yeah,
Um,
yeah. This has got like a few tricks, like the pre-compute and that, but it to actually get it right, I think I actually think this is a lot simpler, the implementation. It's not more complex.
sure.
Uh,
I think
uh,
yeah, I think it's yeah about yeah, I think it's not too bad to implement. I think this is pretty quick, pretty good to implement.
yeah,
Um, so is this right now? I've got two. So we need the index to the info node current to the first and like the pre-computed thing there. So that's that. An info node per level alloc. We'll need to have here. currently we've got a pointer, then the pre-computed cumulative count. That's it, I think. Then from
Yeah,
this we can get to the cool. So this is all good then. It didn't actually bump up our megabytes at all. It's still the same number of
yeah,
megabytes essentially.
cool. And did
Well,
we? I think we haven't yet done that. Our nodes are half full in the worst case,
um,
because that'll bump
no,
up.
we have
Yeah, that'll bump this one and this one up. I think it'll double then.
keynote count. Let's just double like um keynote count maybe.
Mm,
That'll bump up all the things we need to bump up. Also
but
bumps up the index
mm,
size.
exactly.
This is really the one we need to double. Keynote count. The index is also gonna be twice as big
Or
then potentially.
or just this one, Isaac. Keys per keynote, and we said it's half full.
Sure, we can do that too.
Yeah,
The min
sure.
keys per keynote. So we just like rename it to min keys per keynote and then make it half full.
Let's do that.
Cool.
Yeah. Do you want to rename and I'll do divided by two?
I'm renaming.
Cool. The nice thing is
Cool.
it almost doesn't even affect our static allocation because the most
Yeah,
expensive,
it barely changed.
the biggest component is the plus one. That's the heavy part,
Indeed.
which also means if we want to make this
Interesting.
cheaper, we can now reduce our node size. Like,
Oh, well, that makes the query in well, I mean that's gonna be fine though. Like we don't really need to care about making the yeah,
ah,
make the just make that actually makes it cheaper, kind of counterintuitively, because that means there's more static allocation per level. Um, for the info, for this these two things get bigger, but or sorry, these two columns get bigger. The index
yeah,
total bytes and info node per level alloc.
yeah,
Or or index per level alloc is what this should be called.
yeah,
Index.
cool. But it's actually pretty surprising because look what if I undo what I just did, like look at the forest on the
Yeah,
right, 56, 31, 23. Now I'm going to undo
yeah,
it. We were actually already at a
yep,
sweet spot. We actually made it worse going to a smaller node because our per key stuff started overtaking the per node alloc was overtaking
yeah.
the plus one.
Do you want to try making it even smaller to see if we actually get a sweet spot? We could also like plot this somehow in Desmos to see like a nice curve and then find the maximum.
Yeah, but check if we go to a smaller node size, we
Yeah.
actually it actually gets worse. Uh, 32 is worse. 16.3 at 4 is even worse.
Yeah.
And
Okay,
and
cool.
that
I guess we found our sweet spot then. It's
yeah,
also 64 kilo or 64 kilobytes.
exactly, which is always nice, you know.
Yeah, yeah.
You see, this
Are we
also
using the
does.
same thing for block sizes?
We are. Yeah, it's always like a magic number, you know, 64 KB,
Oh
just for
yeah.
everything. That
Nice to
like
see.
for data deduplication, like a lot of the old data dedupe systems, they work on very small chunk sizes. So they take these
Yep.
files, they run like Rubin carp fingerprinting to find dynamic uh, cut points based on the content, like content dependent chunking. So they actually create
Yep.
these cut points so that if the content shifts around, you'll end up finding the same cut points. That's like dynamic chunking. And in even before that, they used to do fixed chunking. So you basically take a file and at fixed boundaries, you cut it up every block size. But the problem is there, as you shift your content one byte, all your chunks have now changed and you lose all your dedupe efficiency. So now they've got this like variable length chunking where it's content dependent chunking, CDC. So Rabin Carp
Yeah.
calculate fingerprints, get this, so you can show, it was very nice. But what they used to do is use like small block sizes, like 256 bytes or 1024, because obviously the smaller your chunks, the more likely you're going to be able to dedupe small changes. But the problem with that is your metadata explodes per chunk. But actually, what like Microsoft did this study where because your chunks are so small, they don't compress well. So if you're thinking of like a lot of the previous dedupe stuff, they examined it like only in a theoretical context without real world systems. But in a real world system, you're going to dedupe, and after you dedupe, you're going to still compress your chunks. So your total saving has to take into account your dedupe efficiency plus your compression efficiency. So what Microsoft found is that if they have a chunk of 64 kilobytes, it's counterintuitive because for dedupe, you're getting less efficiency, but you're also saving because you've got less metadata bookkeeping. Plus, because you've got a slightly bigger chunk, it compresses better. So the net wins was perfect. Like, so I don't know. So ever since that study, I've always thought like 64 KB is the number. Like, because
Magic number.
yeah. So I don't know. Plus that interesting thing recently we saw SPDK. Where you're starting to bypass the kernel for file system for I/O.
Right. Yeah.
64 kilobytes, there's no difference anymore. So anyway, okay, sorry, that was a
Cool.
long tangent, but I always wanted to explain it to you because that's where I got that number. Um,
Nice.
yeah,
Cool. I think. Are you ready to implement this stuff now? I think
yeah,
I'm now happy with it,
yeah,
with our numbers, how they are.
yeah. I mean, we can't, like
Cool.
we've seen, if we go, let's just check here, like for some key sizes, does it make sense to go bigger? No. Does it make sense to go smaller? 23 versus 29. So we could go
It
smaller
does make
there.
sense to go smaller for smaller key sizes, perhaps.
Yeah.
Um. Well,
But then
maybe for 16 is. Let's
how's
make a
us?
total here then. Actually, let's get rid of these two lines because these are now actually not necessary. But let's then just make a total here. That's the sum of these three, and then
Yeah.
see which key size makes most sense.
Yeah.
Um. Oh, perfect. Google's just gonna autofill it for me, I guess.
Mm.
All right. Um.
Because we could do it independently, have different pools, but that's more complexity. So,
This gives us a rough estimate, I guess.
mm.
It's not actually our use case exactly because this is now like assuming that every tree in the table has got 32 byte keys. What
Yeah.
this number is.
So when we plan, there's two things. When we plan for static allocation, we'll have to use the key size of 32. That's going to tell us what we statically allocate. But when we tune these numbers for performance for the read path, we want to plan for key size of 8 because that's going to be the biggest tree where we're going to actually have the biggest accelerator, the biggest root node,
Okay. Yeah.
the biggest index. So this one is actually perfect. Um, if we make this bigger, it's going to get better. Uh, if we look at our index there, it's going to get better and smaller.
Yeah. We take more memory though. But
Yeah,
actually, we yeah. So hmm, stack allocation can be like based on our actual ratios of these key sizes in our tree though. Or no, we still need to assume that it's possible for
yeah,
um all the data to go into one tree.
yeah,
Yes, but this assumes that all trees are 32
yeah,
megabytes.
yeah. So we'll do our static allocation based on the key size of 32, but we should tune our node size for our use case where we're using a key size of 8. Like we want to make the index close to an effective cache line. Here basically our index is going to be 2 effective cache lines in the worst case. But then again, like yesterday, we were tuning things not for a mega cluster. So we want to do key size of 8, not for a mega cluster. We want to actually do tables max, more like
Yeah.
um,
You want to make
divided.
just a copy of these rows down
Yeah,
below?
yeah, yeah. Let's do that. Sorry, do you want to do the copy? Cool.
Almost make well, kind of like insert. I want to like actually insert rows below. I think.
Yeah,
Give us some more space here.
great.
We can have like do another copy.
And then I'll do
All right,
this
so now we
one.
have plenty of space. Um,
So this is actually like our typical cluster size, level 4.
yeah, and so last row doesn't really make that much sense anymore because now we've got it like X is still useful.
Yeah.
But yeah, so in this case, our keynote count is only 2.
Mm.
That's pretty interesting.
Yeah, so
So
we like
are you using it?
underutilizing
Okay, good.
our index. So we want to actually have a smaller
Yeah.
node size. What do you think?
Yeah, make it a bit smaller for sure. Then we have keynote count 4. If we take it just back down to 64 kilobytes, is that
Yep.
then that's then actually perfect, right?
Yeah. Yeah. And as we get to a bigger cluster, then we're looking at
Well, this is still 60 or
yeah. Oh,
this
we
number
should.
isn't 64 kilobytes anymore.
Okay, we
Try and
should
make it
change.
64 kilobytes, right?
Yeah. Yeah.
Make this one too.
Cool. So 64
So
is really like the right number here.
seems like it.
Because yeah, I mean, this is perfect.
8
This
cache
we,
lines, it's perfect, yeah.
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 And then if we even get up to 64, that's not a problem. Then we're just doing binary search on
Yeah,
4 kilobytes.
this seems pretty good. Yeah, I'm happy with this.
And our static allocation is fine. It'll be this number plus our pool where the nodes are half full.
Yeah. I wonder if we need to actually store in the info nodes. I think might need to store in the node itself the number or the count of items in the node.
In the table.
We might need to. I'm not sure if we. I think we do. Yeah.
Yeah, yeah.
So otherwise we can't iterate. Um, there might be a tiny. I'm not sure if that actually affects things or not. Let's see. This would be info node count. This is now like it's slightly different, I think, because we need to add like a +4 somewhere to have those 4 bytes for the count
Mm, mm,
stored inside the node itself.
yeah.
Um, this is we just add this is node size -4 is what we need on node size. I don't think this should actually change anything. I just wanted to make sure we have it in here.
Cool.
Um, I'm gonna be like slightly off. Yeah, that doesn't actually change anything significant. We should maybe use a ceiling here, or a floor here, I guess. Or maybe it should be floor of this. Well, yeah. And then we also need to take then ceiling of the whole thing. All right. This should be correct now.
Okay, cool. It's nice. I was thinking if we've got these spreadsheets like up to date, that later on they'll be quite valuable reference,
Yeah,
to,
especially if we don't get this finished today, we need to come back to it. Then it'll be
yeah,
very valuable to like pick up the spreadsheet and come back and get in the right headspace to implement it.
yeah.
Um, this is now I think correct. Did you look at this formula?
Let me
Yeah.
take a
We
look.
take we, we use the floor to get the number of table infos that fit inside a node, because the
Yeah,
floor because of those padding at the end.
yeah,
We divide the number of tables by that and take the ceiling to then round up the number of nodes, because there'll be one partially full node at the end.
Okay.
Um,
Yeah,
so I think that's all correct now, though.
that's correct.
Cool.
You want to take a look at the
And keynote
forest?
probably need the same thing. I'm
Yeah,
going to take the ceiling here as well,
yeah,
the key for the keynote count.
good.
And
And
for the 16 ones to make the numbers a bit nicer. Now we get like nicer numbers across the board.
yeah,
Um,
min keys also.
yeah,
We've got
these will be
a
floored. Yep.
floor.
Oh, I found the wrong one. Whoops. Okay.
Cool. Do you want to take a look at forest pool? I basically did,
Oh,
it is tables max times the
yep.
table info times 2
Yep.
because our info nodes are half full,
Yep. And then in
divided
megabytes.
in megabytes.
Okay. Um, that's gonna be then the pool of only the table info nodes, though. And
Yeah,
that doesn't include the key nodes.
no, the key nodes are separate. So yeah, we must make that clear. Maybe we should just add it all together.
I
Do
think
it
we should
all in
add it in
one.
here as well.
Yeah.
Shall I add it?
Yeah, you go for it.
The same thing, but just with key nodes instead of or key size instead of table info size. Um,
Oh, it's we've got our keynote count. So it's keynote count times node size, isn't it?
oh yeah, that's all it is. Shouldn't the other one be info node count times node size then?
Yeah, because infinite count, that's like the max, yeah, that we would have. Okay,
Yep.
okay, do you want to do that too?
Or
Both of
hold
those.
up, I didn't divide by 224.
Hmm,
Add that one too.
yeah.
Um, and then info node count times node size, I believe is what this should be. Well, actually, I don't know if we add the half full part for the info node count. I don't think we have. Before I do that, I need to add that in here for info node count to make things half full. Um, so just need to divide by 2 again. Yeah,
Yeah. Well, I think that, okay, yeah, didn't we do that already?
or multiply by 2.
We did
We've
it
done
for
that for the keynodes, but not
keynotes. Yeah,
because we did that in min keys per keynote, but we didn't really do the. We've done this one all in one box. So I'm just gonna multiply
ex
by 2 here.
exactly, yeah. Cool.
That'll actually change things a little bit.
Yeah,
That'll be yeah. It's gonna increase our alloc by a little bit, especially for the big ones.
yeah,
I think it's still fine. Our strategy doesn't scale, that's not like a magnitude difference.
yeah.
And forest pool, this now needs to use yeah,
Infinite count
node
times
size,
node
or
size.
yeah, just infinite count times node size. Oops, okay, that seems right.
Yeah.
Cool.
So then what we're looking at in total is going to be, if we're going up to level 6, then we're looking at those two together, the 52 and 544.
It's 600 megabytes.
Yeah.
Not bad.
Hmm.
Right? That's within bounds of what would be reasonable.
Yeah.
Um,
Yeah.
like
It's
anything less
good.
than a gigabyte is quite good actually for addressing 100 terabytes of storage.
Yeah.
Um,
It's good. we should, I think what we'll probably want is a way that at runtime, the operator can set the max level, and then we can see in the superblock how many levels we've gone to. So then at runtime, when you start the cluster, it doesn't need to do so much static allocation. It only needs to go up to like level 5 or level 4, because that's a lot of memory saved. Most clusters only have to do 70 megs. But then
Yeah, we could definitely. I think we should just start with doing all of it, but then we can do that kind of optimization later as an extra
later,
feature.
yeah, exactly.
Um,
Yeah,
I think
yeah.
that would complicate things at this point, though, to add that feature before we're done with the whole. I think user interface is something that comes later in general.
No, no,
We want to get to the core.
I'm
I agree with you
also,
there. That'd be a good feature to have.
yeah, I'm only thinking way. I'm not thinking we should do it now because
Cool.
it also kind of undermines the whole thing about static allocating. You can go up
Yeah,
to
it
that.
does.
Like,
That has to be done really. That has to be done right. We need to like give that some consideration for sure. But I
yeah,
think this works out. It also won't be that bad because we actually don't. Well, this 400 megabytes is a little bit too high because we don't have all 32 um trees using 32 byte keys or all
keys.
30 keys using 32 byte keys.
No,
But that's so. But the forest pool would still have to be just this big because we assume that any tree could take up all the data.
exactly.
Just to make things robust. But
Yeah,
this also, I think this is still fine really for mega clusters.
yeah,
That's totally reasonable
yeah.
and quite good actually.
It exactly. And then, like on top of this, we're going to have the disk cache, which will be like 32 gigs easily for a server, or 16 gigs.
Yeah, yeah,
Um, so,
exactly.
and then
Cool.
later on, we can always see maybe the operator says, well, I only want up to this, but I mean, that's way down, like you say. We don't do that now. Cool. So how you feeling, Isaac? Is this
Yeah, I'm
my,
feeling this is ready.
yeah,
This is cool. Yeah.
yeah. Do you think, is this got that bidigital jazz vibe where it's fast,
I think so.
simple?
Yeah.
Um,
It seems very. Yeah. I'm happy with with the. It's just gotten even flatter, but
mm,
without really losing that much. Yeah,
yeah,
and just going from a key node to an index node is not that bad. Um, we know in constant time. Well, for on the well, so let's just consider the lookup path real quick. So we know in constant time the index in the key node because we found it. We've done a binary search inside the key node to find the exact key, and we know that place that index inside that key node. Then we add that to the stored count of indexes or items stored for this keynote starts, which we've got cached. That's still constant time. And then we, in constant time, have also stored in our index the index of the info node that contains the first key min in the key node we just looked at. We go there in constant time. And then we know for the start index of the first index in that node because we know already we've pre-cached like the number of items in the table in the info segmented array to that point,
yeah,
and then
yeah,
we need to iterate um, potentially. I think it's only like four. There's some constant number of info nodes that it might not be constant because of this like divide by two thing, but there's a
yeah,
constant upper bound on the number of nodes we have to iterate there,
yeah,
which is not that big. I think it's something like it has to do with the ratio of table info size to key size,
exactly.
um,
Yeah.
and it's not that big, I don't think. But I think that's all good. I'm happy with that.
Okay, and the nice thing is we're going to iterate without doing key comparisons. We're just literally going to iterate skipping
Yeah,
over the
we're gonna
nodes.
skip the first few nodes probably because we can just like see that
Yeah.
and each node stores its count um, in the table nodes at least.
Mm.
In the table info nodes, they need to store their count, so we can skip over them. Um, yeah, That seems
I,
good.
I was wondering if we couldn't just store the count as part of the cumulative count up to that point. But that gets
We could store
tricky
two numbers.
if we rebuild.
Yeah, we can. Is that like wondering if we can calculate the count as part of from the cumulative count? I think we can.
Yeah.
If we like take the subtract the next one from the current one, essentially to find the count.
Mm.
Um,
Yeah.
we'll just see in the optimization makes sense, or if it's in an
Yeah.
optimization, or if
Yeah.
it's too complex or whatever.
Yeah.
We could definitely do that though. That makes
Yeah.
sense. Um,
Nice.
yeah, we'll,
Thanks.
we'll see
Thanks,
how it works off
DJ.
alignment and whatnot.
Yeah.
Yeah.
Awesome. Yeah.
Well, DJ
What?
got us started on this, but then we took it from there. But yeah,
Yeah. He gave us the what if question, and then
yeah,
we said, well, how could we make it work? Like, just what would it look like? What if? Well, let's
yeah,
run with it, and let's just try and solve it without even evaluating it. Just like, what if? Make it work, and then let's see. Okay, pros and cons. Does it work? Yeah.
yeah. I think we ended up allocating a bit more memory than we did with the other strategy,
Yeah.
but the code will just be simpler. I think that's the main advantage, is just make the code simpler. Because I'm
Yeah.
confident the other strategy would have worked as well. But like I said at
Yes.
the beginning, we're now just like comparing other strategies that would also work to see if they
Yeah.
meet our constraints and if they have them some advantage, such as simpler code.
Yeah, exactly.
Um,
Yeah. So you
cool.
think we're getting a bit faster with this and simpler? Uh,
I'm not sure if we actually get faster. I think the other one might actually be a tad faster. I'm not sure. It's really hard to know without a benchmark.
mm,
It's not clear to me either. Actually, yeah, it's not clear to me which one of these would be faster. I think they're mostly equivalent. They mostly, the binary search is the bottleneck in both of them, I think.
yeah.
And then there's some different constant overhead. And the first one's like some pointer tracing to iterate over the levels to get to the bottom level.
Mm,
Um, and whatnot. Maybe it's a little bit more branchy. Well, in this one, you then have to do this iteration once you found the key to find the right table info,
mm,
um, which is also a little bit of overhead. It's not really clear to me which one would be faster.
yeah. I did wonder if we couldn't increase our root node um, a little bit more so that we do less binary search in our actual key node, because our key node size is 64 kilobytes.
Does that actually make things faster though?
Well, actually, we
That's just like,
can't do that because I thought it might make it fast, but I don't think so. So the thing
I don't
is
think it
that
does.
yeah,
You're still doing the same number of comparisons. Um,
what I was trying to exploit was a better balance of effective cache lines. So the index has
okay.
one effective cache line. The keynode has a few more. So I was thinking, what if we can do like two effective cache lines and more equal? Um, be, but the thing is, we can't do that because we would have to decrease the node size, and we're already in the sweet spot for node size in terms of everything, static allocation
Yeah.
and so
Cool. So I think I think we're good with this then.
yeah. So we
Do you want to
do
take a
like a.
break and then start implementing it? Yeah.
I was just going to say that. So like, should we be back on that in 5 minutes time? Uh,
Sure. It sounds good.
okay, catch you now. Get out.
You
Yeah,
can.
ciao. Hey, Isaac.
Hey,
Uh,
so are we ready to start implementing this?
yeah, you think we can knock it out like in 2.5 hours, and that'll be pretty awesome.
We'll see. Yeah.
Yeah,
Maybe we can get it done, but
sweet.
I'm not sure we can get like exhaustive tests that quick, but we can probably get that core implementation mostly done.
Yeah,
Um, cool.
yeah, let's go for it.
All right. Do you want to like let's like leave this file. Let's do a new file. Like this one's like kind of got like the structure of the old one kind of
Yeah,
nicely. We just like leave that for now until we're like totally confident we can delete it.
yeah,
Um,
I
so I'm
like that.
gonna make a new file. What do we want to call it? It's not really a tree anymore. It's like a level, just a manifest level. Man, I think that'd be a good better name for it.
Mm.
You can copy stuff from the old file though. You start by copying everything, and then we close that buffer. Okay, and now clean out the struct, I guess. Or well, we're gonna need similar calculations here, but we'll just have to change this stuff around. There's no more root node for sure. Um, Data nodes. This actually is gonna be the same calculation we used to get the total number of table info nodes, I think. Something like this. Count max table info per index node. So this is gonna be similar. This stuff's all similar. It's all related, but we just
Mm.
need to modify it to fit the new requirements.
Yeah,
Let's rename root node to index node to make this one. This is our new or just let's call it just index. It's not a node. There's only one of them.
yeah.
This is the index, and this will store
Maybe we should call it key index or keynote index, and then we'll have keynodes.
Keynote Index. Yeah, that's good. Yeah. Well, it's really it uses data nodes as well though, because it stores like in like um we're in a cache also then the info node indexes that correspond here. It's just like our general index, I feel like.
Yeah, I thought that could actually go into the keynote because we only need that when we get to a keynote once we've completed our search.
Um, hmm, I don't really. I think we have introduce padding here potentially. I think. Oh no.
Yeah,
Right
or
now we're
we could store that out of band. But I think that the keynote index we want to just have keys in there. So because that's more about finding the keynode. Once we've found the
right now
keynode,
we've got where's the keynote index? That's this one. Yeah. Right now
hmm,
we've got keys or keys. No.
yeah,
Hmm. Yeah, keys. So we got keys. That's this. Then we got a
hmm,
pointer to the key node. And we've got the cumulative count for that key node before that key node. Then we've got the index into the first info node matching this with the key min. And I was just gonna do that as all structive arrays inside the index.
yeah,
Alloc.
okay, okay.
Are you happy with that?
Yeah, I don't know if I understand if we thinking the same thing. Um, I'm just thinking like where we do the actual search on the accelerator itself, the memory is only going to be 8 keys, like for level 4.
Yeah, well, we would do destructive
Yeah.
arrays here, so there would be a slice of
Uh,
eight
in,
of 8 keys.
okay. Okay, cool. In all inside the root. Okay, okay, cool. I'm
Yeah.
with you now. It's that same difference from earlier. Yeah.
Yep.
So you just want to call it the index overall.
I just want to call it the index because it indexes all both everything kind of.
Mm,
Then here, there's no more child node stuff. That complexity is gone too. That's nice.
mm.
So we've got first just keys, or maybe key node, or just min, or maybe just call it like min keys, um, or min key. I'm not sure. So we need here
Uh,
like keynote count.
I would then call it like keynode keymin. So it's the keymin of each keynode.
That works, yeah. And then here we just got it's type key. And this we need a keynote count max.
Yeah.
We'll need to like, yeah, I don't know about this variable. We'll maybe put this inside the keynote struct. I'm not sure. So it'd be nice if it was like keynote count max.
Yeah.
But
We can always do this as like a very
yeah,
rough, we can do this as a spaghetti pass. So we like just cook the
yeah,
spaghetti as quickly as possible. And then next year we'll come and do the
sure.
bolognaise and the sauce and dish it up and plate it and test it.
Get the names perfect. Get all like
Yeah,
the names aligned.
yeah. If Larissa is watching, we really need a good recipe for bolognaise. I've got like a South African one, but wouldn't mind a proper Italian. Yeah. And
Keynote pointer.
Nipsey, if you were still on, I had some good news from my mom. She's actually cooking bitterballen today. So like the
Nice.
Dutch cricketer, so I'm pretty stoked for Christmas. We doing bitterballen. Yeah.
All right, keynote pointer. Then we need a name for these. So we need the key node start index is what it is.
Yeah.
That's the perfect name for it, actually. Sweet.
Yeah. This
That's the
replaces
cumulative
cumulative
count thing.
count. Yeah. Yeah. Cool.
Start index is
That's
good.
perfect.
All right, and then we
Perfect.
need info node or or info node or first or min info node or info node min, I think. Index or info node min is now a U32 indexing to the slice of info node pointers. Um, we need info node. Well, so these are all parallel structural arrays, and this is also in that structural arrays thing. But then we also need a separate one for info node stuff. And for this, we need then just info node pointer. I'm gonna leave this one unfinished for now. This is like to do. I don't know the name for that one yet. So we need info node pointer, which is then info node count max. Info or then we need the info node start index. Same thing here. I think we also need to make this different. I think this should not be like using arrays. This should all be using slices, I think. And then we allocate them separately on startup with the right maximum sizes. There's no reason to
Okay.
allocate like one block for all of these. That doesn't really make sense.
Okay.
Um, these should be allocated because they are now pretty big, unlike what the root node used to be. Um,
Yeah. So that's going to be
so
pointed to an array.
yeah, right. That's perfect. These should all just be pointers. Okay, and now what's our name for this variable or this one? There's also U32, and this is now the first info node that could hold the key min.
Okay. Maybe
Uh,
then it should start with keynode as the prefix. Keynode
yeah,
to info node.
node.
Keynode keyman info node.
Okay. Yeah, that seems kind of like that's fine for now. We'll come back to it.
We'll come back.
Spaghetti, right?
Yeah, spaghetti.
Yeah,
Yeah,
it's nice and explicit at
we'll.
least. Um,
It is. It shows you all the things going into the sauce, and then we'll
yeah.
reduce that sauce. Yeah.
And so I think we should put this also like just straight in the do we also need Keynote count then?
Yeah, I was wondering about that. If we do have keynote count, maybe we don't need to do optional pointer on the keynotes.
It's more like just for safety, just we can just like zero initialize it and then have have safety like
Okay.
we never actually compare these with null. We're just going to
Yeah.
be setting them to null on initialization and then always using the dot question mark to assert that they're not null.
Okay.
Um,
Okay, cool.
maybe I shouldn't
Spaghetti.
do that and just like rely on the built-in safety checks though and just not make the asserts explicit. I think that's actually that's more idiomatic actually. Yeah, you're right. Um,
Yeah.
then we initialize them to undefined. So that's the thing. Undefined is now it's currently got it's like a few. Yeah, I think it's currently safer with the current Zig compiler implementation. It's safer to do it this way actually.
Yeah. Yeah.
Um,
Do that. Let's do that. Yeah, that's motor on. Very good.
and now I'm gonna take these out of the index and just put them in the struct. That's what I
Yeah.
think we should do.
Yep.
Because I've now got something's gone wrong here. Um,
It's the,
oh, I see.
I think, yeah,
We've got fields down here as well, which are just out of date. They don't need to be there.
split.
And because you can't have decals between fields, it was giving us a syntax parsing here. Here, it's also in the
Exactly.
grammar now, which is
Cool.
um.
Yeah.
So now we need key node count max and index node and info node count max. The key node count max is going to be um A2 over E28. There's tables max divided by min keys per key node. So we need min keys per key node here. It's kind of similar. Um, do we need this comment here? Or key keys key nodes are a segmented list. Okay.
Cool.
We also need like a +1 here though, right? The last node could be not entirely full or something like that. I'm not sure.
Yeah.
Um,
Yeah, it's the +1. That was our +1 overhead that we, so that there
yeah.
should be a plus one after that.
Because
Well,
this be so min
min keys, that's correct. And then when we actually calculating the node count, that's where we do a +1.
okay. So keys per key node is going to just be divided by 2.
Yeah.
Are key nodes really just an array of keys now?
Yeah.
Do we need anything else in there? I think they really are just arrays of keys. Yeah. Nice.
Yeah.
Cool. So this is just node size divided by size of key divided by 2. Cool. And now we need the next thing is going to be we're going to go straight to keynote count, which is then the tables max divided by this number. LSM table count max divided by min keys per keynote. There we go. We've got our keynote count max. Onwards. Now we're going to do the same thing for info node count max. Info. Do we need the same comment again? As we might as well. Let's keep it like
Mm.
spaghetti-ish.
Yep.
Um, now we need table info size. Info node count is just the same thing. well, I've subtracted 4 for the actual info nodes are a bit bigger, I guess, because we need to have like the count inside the info node. So maybe we should have a keynote and info node structs real quick first.
Cool.
Keynote. This one really is going to be just an array of keys, I believe.
Yeah, that's it.
No data nodes or anything. It's just key.
And it's bounded
Then we
by the
have
node
here.
size, and it doesn't even have a count. Yeah.
Yeah. No count.
But it makes
Do
sense
is
to
putting it
put
in the
count.
struct even worth it?
Oh,
Hmm?
it's actually, yeah, it's actually fine to have it outside the struct keynote count max. Like we've got all our
Yeah,
stuff
yeah.
in one place, all our calculations. Yeah.
You mean up here?
Mm. So,
Or this is like key count max inside the struct now. So just count or count. This is just count max of the keys
okay,
inside
okay,
the
okay.
keynote.
Yeah, that makes sense.
So we actually need
Yeah.
node size. We just need to get rid of this this minus U32, and then we're good.
Yeah.
And make this proper. It's just
Yeah.
size of key.
Yeah. And we need to, up above, Isaac, I think we need to double check our floors and seals. We might have only been using floors.
Uh, yeah, I haven't done the plus one or the ceiling here yet.
Okay.
There should be div seal. You're right.
Okay.
I was gonna do these to get them done and come back to that calculation, but I didn't say that. I don't
Let's,
think.
okay. No,
'Cause I
cool.
wanted to make sure I wanted to figure out the table size, the table node size, to be able to do that
Cool.
properly. Uh,
Let's do that.
info
Yeah.
node. This is now gonna not store any of this stuff. We do need a count though. Actually, we do need that same stuff. Cool. Get rid
Exactly.
of
Yeah.
those pointers. Because now we just iterate across our array of pointers to these things, which works out even nicer.
Yeah.
So we don't store pointers there. We do store the count still, but it might work out with padding. I don't know. We'll see.
Yeah.
So
Yeah.
count max. We still need the same calculation here essentially, but we don't need the 2 times size of pointer. We just need the size of U32. But most of this stuff is still good to go.
Yeah.
128, 2 size keys, and 3 size U64s. Then
Yep.
data size divided by table info size.
And we want to do a floor there, so that's correct. Well, I don't know what
Yep.
if you were thinking anything else. Count
We end up
max,
with a little bit of padding, but that's fine. Okay.
fine.
And so now we know the table info. So info node count max is in the number of it's really capacity. I think is a better name for this.
Okay.
Info node that capacity reads way better. It's count max. Info node that count max seems like the number of info nodes maximum, not the number of data each info node can store. The info node at capacity is way more, or it seems more less ambiguous.
Yeah.
Um,
The one thing with capacity is I'm never sure, is it bytes or is it a count? So the count is like crystal clear. What it
I think all the Zig dictionary library stuff treats it as a count. Um, I think
exactly.
in
Yeah,
Zig
no,
it's a count.
yeah,
At least that's
it's a
the
count.
convention here. I
Yeah,
think
yeah,
I'm happy with this. I think
yeah.
that's yeah.
I actually prefer count max here because it lines up with count.
Okay, yeah, you're right.
Yeah,
That is
and
nice.
it's also shorter, like uh, and less syllables. Yeah.
Cool. Size of info node
Yeah.
is equal to no size. Okay.
Okay.
And then
And then
do we really need this
oh, sorry.
keynote struct? We could also just use an array, but maybe this is nice just to have the type for it. We can just bitcast do the same thing.
Yeah,
We can come back to that if we decide it's a bad idea in the end.
yeah,
Now we gotta fix up these. Um,
yeah. It's nice
remaining
having.
keys per key node. This is now keynode.count max. See, this is why I don't like count maxes because now it kind of conflicts with this variable name. That's why I was liking capacity
Okay.
more.
Okay, now I understand. So maybe like maybe the problem is that we should be saying key nodes count max. Like what is the count of the
Fair
key
The
nodes?
two,
Like,
like the one layer difference I also don't like though. I think those things are
yeah,
too easy to like read over when you
yeah.
come back to this code. That's why I was
Okay,
thinking we just need a different name for the
yeah,
capacity of each key node.
okay. Or we could just call this key nodes max.
Yep, that's better, I think. Also shorter. I like it.
Yeah,
Okay, so
yeah,
now we've got min keys per key node is key node count max divided by 2. Um, that's properly flooring. And then we need to take table count max divided by um, min keys per key node. This will give us and then we need to add 1 to this. And this should be ceiling division. Or, is that right? Or are we overcounting then?
Um, I'm I'm thinking table count max. Yeah, we want to do seating division then.
Yeah, we
Min
need, still need
min
a plus 1
keys.
though. Um,
Yeah, +1.
do we really need that though? Because we just did ceiling division. Um,
I think we don't need the +1. We only need the +1 when we do the static allocation in the pool.
yeah, I think you're right.
That +1, yeah, it's off by ones are hard. Eh?
Oh yeah. Give seal. It's safer to just have it because then like the worst thing happens is we have one extra. Um,
Yeah,
I'm
yeah.
kind of
Okay,
inclined to just like leave it here for now and then come up leave a to do to see if we can get rid of it.
let's
But
put
I
it
don't know
back.
if it's
Yeah, let's put it back, and then we understand it better later.
here. All
I
right.
was thinking we should either say segmented array or unrolled linked list. Because if we say segmented list, then people think we're doing this linked list vibe. Yeah.
Like everyone can array better. We don't want to market it as a linked list.
No. Yeah. Shame. Poor linked list gets such a bad rep. And then when it
Or
tries to
linked
be
list. I love
unrolled,
inclusive data structures.
yeah, 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 yeah.
Min keys, but unrolled linked list also doesn't really make much sense to me somehow. I don't know.
No, doesn't have
I think
segmented
segmented
array
array
is
is
a
better.
much better picture. Yeah.
Min keys. This is the wrong calculation completely. This should be min infos for info node. This is
It's like
then
putting
this size.
strawberries in the bolognaise instead of tomatoes.
Yeah. Info node. I wonder if that would taste like strawberry pasta. That sounds really weird.
I once went for dinner with a few friends at a friend's house, and his sister
Yeah.
like cooked up the dessert, or she made the dessert. She was so chuffed with this dessert, and she brought it was like all these. It was fantastic. It was strawberries, like really nicely sliced, and they had
Yeah.
been macerated, and it was beautiful. Only problem was she had cut the strawberries with the same knife that she used to chop the garlic in the other cooking process. So all the strawberries had this garlic taste, and yeah, that was so.
Oh
It
no.
was like almost like a spaghetti with strawberries in it. Yeah.
That's really funny. Too bad
So
though.
everybody was just tasting and seeing, and we were all trying to check like, are the strawberries garlicky? uh, uh, yeah.
That's funny. All right, so we've got our infinite max, we got our infinodes, they're done. Count max is correct. Um, Keynotes, count max looks good. Cool. So now we've got our data structures done, I think.
Mm.
Are you happy with that?
Yeah, yeah, that's cool.
Okay, I'll duplicate
Maybe,
this to view again.
I don't know if I'm getting in the way of just hashing this out quick, but maybe I think you're right. Like the keynote count max, it makes you think that it's a count of the keynotes rather than like keys
Yeah, it
max.
really does.
Keys keys max would be better, but that doesn't work well for info node because we don't have a plural
Exactly.
for that. So
Like
capacity actually
info
is,
back. We could use info. Well, yeah, and just capacity works better here for sure.
yeah,
Um, are you happy with
info
that
node.
now? Or
It's better. Yeah, sorry about that. That's much better. And
no
then
worries
do the same for key.
for consistency.
Yeah,
But I think
cool.
keep sticking with Keynote's max. We can make this now go back
Chris,
to Keynote count max, but I think just Keynote's max is nicer. It's a little bit
it's
shorter.
fine. Yeah.
Cool. Now we've got our data layout. That was quick. Now we're on to, well, these functions are all out of date, but we can like, yeah, let's get rid of this one.
Yeah,
We need,
yeah,
so we want like an insert and then a query. Do you want to do query first? Um,
yeah.
I think that's, um,
That's the
so is this, are
best
we
way to
going to do,
think of it. Yeah.
yeah, get tables API? Are we going to do the get tables function first or the, like just do the iterator that returns us a range of keys?
Yeah, like do it in a few steps. So we could have a few helper functions, like one function to
Yeah,
search binary search the accelerator for the keynote index, another one search the keynote index for the actual logical index, another one to jump to the info node, and then we can at the end wire it all up into our iterator or whatever you feel comfortable with.
Christoph says in history they made pasta with marmalade.
In Hungary. Yeah, Luis, I was asking just now if you've got a good spaghetti recipe for bolognese because I actually put a little bit of apricot jam into my bolognese sauce. I don't know if that is allowed. Plus a little bit of Tabasco, paprika, uh, but I don't know what you think is apricot jam, okay?
Yeah, I think he's got a video in Zig Showtime of a nice pasta recipe for summertime. I don't know if you've seen it yet, but it's got lots of veggies and
Yeah,
whatnot.
is that the one from the foundation launch with making an espresso and
Exactly, yeah.
making the zig? Yeah, that was fantastic. Yeah. I was thinking like Yakub and I were doing some of like our cappuccino latte art shots, you know? So maybe next year, like I can stream from my house and we can actually I'll make some espresso on the stream with my new machine. Yeah.
Nice. All right, so iterator. Well, I'm not sure how to start this. I think yeah, because we know the steps we need. We need the first step will be just going from. Well, we'll take a key. We just look at the key min here. We only look at the key min
Yeah.
until we actually get to the table info. Then we start looking at other
Yeah.
stuff. So
Yeah.
really, the first step is going from key min to the place in the table info iterator. Um, I'm
Yeah.
thinking like a little bit bigger than your steps were. There's
Yeah.
two
Yeah.
main steps, which is the first is to go from the key min to the right place in the table info um, segmented array, and then
Yeah.
the next step from there is to iterate until the end of
Yeah.
the range we want to look at.
Yeah.
Um, so
Cool.
we want to say, so maybe we just do the first function. Maybe we make it like not very fine grained yet because we're not really sure what will make sense to abstract or take out. But this will
Okay.
just take a key min.
Yeah.
What do we want to call it? Like,
Keynote
um,
index.
or
Keynote
I want to
index.
call it like info, um, info list search start, and this will then just take us from the key min right to the place in the key info node just where to start searching. Or well, yeah,
Yeah.
let's just do keynote index. I think you're right. Um,
Yeah.
change my
Cool.
mind. Key
Cool.
or not keynote index, but yeah, I
It
think it made
it
just like
is it is the Keynote
just
Index. So given the key, do a binary search and get the Keynote Index. That's our first step.
okay.
Keynote is also fine. Either way. Okay, let's go. We'll
Keynote
reduce
index
the source. Yeah, we'll reduce the source.
key. So we'll turn a U32. So now we just do binary search. We need binary
Yeah,
search. What's that
yep,
called? It's just LSM binary search.zig.
yeah.
Um, binary search. Oops. Now we're going to search from. We're going to do binary search. Well, it's not going to be any completions for this. We need key value, key from value, and compare keys. The key and value are the same here.
Yeah,
I wonder if we want like a separate version of this where it kind of wraps this
yeah.
for only keys and
Shall
returns
we
an
just
index instead.
shall we just copy pasta to and just tweak this to exactly what we need, and then we'll test it all at the
Sure,
end.
yeah.
Yeah,
Well, I don't know. I'm not. Well, we want a separate version of this that takes not instead of a value slice, it gives an index. We want to
yeah,
then get rid of this key from value stuff.
yeah,
Um,
exactly. We could literally just copy this binary search, make it as a function in our
sure,
file, and later on we'll come back and
cool.
refactor.
Binary search. So it's no longer public. This stuff's all like part of our type already. So this
Yeah,
just takes a slice of keys,
nice.
keys, or sorry, const key, and it returns at U32 index because we're gonna be, we might as well
Yeah,
cast it inside and to hide some keys.length, some values, keys.length. Might as well return it. I don't know. Should we return a U size or a U32?
U32, U32. We'll come back later and we can tweak it. Uh,
Okay. Um,
we just need to show the
we
rough
don't need keys
idea
from
here.
value anymore. It's just
Yeah,
keys mid. Um, then this
that's great.
returns an index.
Yeah.
And also returns an index. Okay, cool.
We don't
That's all
even
it
need
is.
this stuff doesn't even need to be correct. We'll come later and catch all the compile errors and
Doesn't even need to
we
be correct.
we just like I mean we literally throwing spaghetti onto the walls here. That's all we need to do. Just stick it in the right places.
All right.
Yeah.
Yeah, you're right. We just want the overall structure of the code really, and
Yeah.
then we want something that might not even not compile, but we can then start testing. Then we come back and then fill in the gaps and whatnot.
Yeah.
We got binary search now though, so this is already a good start.
Yeah. And it
Yeah,
probably doesn't have an overflow bug in it. I mean, it's got that
probably
part
not.
right. But yeah.
We've already tested the binary search algorithm itself. We just like tweaked some minor things just now. I think I've got this done all right. It's mid there, yeah, and
We've got a
offset there. Yeah, that's all
U size U32 mismatch, but that doesn't even matter. We'll fix it later. Like it's good for now. 'Cause we let's keep
good. We'll
going.
stick an incast there. Okay,
Yeah,
we can.
yeah. We just keep speeding here. Yeah,
Okay. Um, so Keynote Index. This is now. So we're gonna do binary search. This is binary search level dot key, or what do we call it? We call it keynode keymin.
Yeah.
And then keymin. This seems weird because it's now like not plural, but let's just leave it for now. It's fine enough.
Yeah. Yeah.
Um,
Cool.
cool. And we got index, and now what do we return from this function? We now got our index into our keynode parallel arrays. Now
Yeah.
return well now we're gonna do a return. Now we're gonna go look up the pointer of the keynode and do a search there.
Yeah.
Um,
But we can already just
so now we're
return
gonna
this
do.
index. We can return this index out of the function, and we're
I think we
done.
should do a bit more work here. I think we should. We
Okay.
want to find the keynote. Or we just do the maybe just make some key index. They'll get the actual index in the keys segmented array. Because it's not that much more work. We just do one more
Yeah.
binary
Yeah.
search. Um,
Cool. Cool.
this is node index or key node index maybe, and
Yeah.
we'll have
Yeah.
like just key index equals binary search. Now we go to level dot key node pointer.
Cool.
Um,
Keynote index.
So we need to know what the count is at this pointer. I think we can obtain this though from the keynote start indexes. We subtract this one from the next one from this one or something like that. How does that work?
The start index, that's more to do with,
Well, can we just store counts then as well? For
we
now,
can still, yeah, let's do that for now. And then later on, we'll come and fine tune all of this.
because we can calculate the counts from the start indexes, but it makes the code a bit more complex.
Yeah.
Counts or count. Ooh, that's not. Or um, that seems like a weird name. It doesn't really work. We got
Mm.
keynote count and
We
so
should,
keynote.
I think what we should do here is say keynodes count, keynodes key min, as if it's all structive arrays. And then the actual field is singular. Oh, it doesn't help us.
Okay. No.
Uh, okay.
Like if we index it, maybe it's okay. It's
Yeah.
keynote count, but it's an array, but it's
Yeah,
still got
that's
the
fine.
same name. So just leave it.
That's fine.
I'm just gonna leave it keynote counts for now, and then we'll come. We're gonna
Yeah.
get rid of the field anyway. But,
Yeah.
to do get rid of it. Okay. Keynode pointer. So here we need const keynode slice equals level keynode pointer.
Keynote index.
Make this just I,
Yeah.
because I want to make it line shorter. Um,
Yeah.
0 dot dot level keynode counts I.
Okay. And then we can add it
All
to
right. And we
do
got,
just after binary search. Our first binary search to do double check for out of bounds if the key isn't found. Like just think through what if we've got no key nodes or like to do think through out
oh
of
yeah,
bounds stuff
we need to handle the
around I.
negative lookup too. We're not doing right now.
Yeah,
Um,
yeah. So we could just say yeah, think through out of bounds negative lookups, etc. And then we'll come back. Cool.
Keynode pointer is now keynode slice that we pass in. And we pass in then the key we're looking for, a key min. Thing we're looking for still, and then we return this key index. Key return.
Yeah.
Now we can get the key index given the key min and the level. Then we need to go from there to the table. So now we're gonna need another function to get the table info.
Yeah.
Or well, I kind of just want to be the iterator now. I feel um, like this is the only thing we need to do at the start of the iterator. Then everything else is just incremental over the steps of the iterator.
Yeah,
Well,
there's one more thing, like a routine we could use. Given the key index, get to the accelerate the iterator, like figure out where to start the iteration. Uh, but okay, we can do that in the iterator if you like.
I think that kind of we need to know what state our iterator needs so we can accelerate.
Yeah.
Um,
You see,
I
what's also
think.
nice if we do it as a routine is we can test these individually outside of the
Right.
iterator.
Yeah.
And these
I
ones are
think.
quite nice as little testable units.
Yeah. What does the binary search even return? Um, if it does not found? Totally forgotten.
Yeah,
What are we like testing if it's not?
it's going to return the index of the thing that's greater, or
Oh.
else
Like the
and our
index
key
just
in,
like one greater than.
yeah, I think we kept
Maybe
it the
like a
same
test
as
case maybe.
Eitzinger, so it's the smallest thing that's greater than or equal to. But we should actually be showing it in our test case.
Probably. What do we have it in here, I guess. Um, spec index. Okay, so yeah, so we've got three parameters here. We've got keys, the keys we're searching for, and then the indexes we expect to find or get
Yeah,
result as a result. So yeah, you're
yeah,
right. So we have this is our place of keys. Then we search for 0, we get index 0. We search for 1, we get index 1 because
yeah.
that's like the index just passed. And then we search for 1
It's
again, we get index, or we search for 2, we also get index 1. For search for 3, we also get index 1. We search for 4, then we get index 2. So yeah.
yeah, yeah. And then our key index function, we need to actually take the cumulative counts into account, or we only currently returning the index from the binary search in the key node, but we need to take the counts of the
Oh yeah.
previous key
So
nodes
right.
into account. Yeah,
So level dot key node start index I plus that,
yeah,
right?
yeah, that's it.
And then this might actually be fine to just leave it like this, because then what
Mm,
will happen is we'll get this is like the branchless way to do it, I think, because we then we end up with an I with the keynote past the one where it might have been, I guess, and then
yeah.
we may want either to abort early to avoid the second binary search, or I don't know.
I
We'll come back
think
to
we
this.
should, yeah, so long as it's safe, we should just do everything that we don't even stop to think. We just do it as if it is
Okay,
gonna
yeah.
hit. Yeah,
And so I think there's might be an out of bounds though if you like search for the last thing in the array. Is that right?
yeah,
If we search for Well, so if we search for 13, that's bigger than the than 11. So we get
yeah,
6 back. It says 0, 1, 2, 3, 4, 5. So you do get past the end there.
yeah.
Okay. So
I
we
think
do
we
need
should
like a
add
branch
it.
there. I think that's to make it safe.
Yeah, we should add it to do in this binary search file. Just quickly, like add it to do a test search on empty slice because we don't have that yet. Uh, wait,
Good
yeah,
idea.
cool.
Cool. Out of bounds. So right now we're just gonna assume positive lookup and do that code path, I guess.
Yeah,
Um, no, I think we should start the iterator now and see what state we need to iterate. So we need
okay,
an index into the we need the keynote index that we're looking for. Well, there's two iterations. We need one more thing to like start the iterator. But let's just assume we've
exactly.
already found the info node. So let's say we've already found the key in the info nodes. Then what we need to iterate further. Then we'll like find the function that ties these two things together.
Cool.
Um, Then we've got like current info index. We can just call it like info index, I guess. And then we're going to need info. This is an index into this array and
Mm,
this array.
mm,
And so, oh, I've asked this before actually, but um, I think it's still fine. But if we split an info node towards near the start of this array, we're going to need to memcopy all the pointers, I think,
yeah, yeah,
which I think is fine.
that's fine.
But we need to be aware of that.
Yeah, yeah,
It's only
yeah,
when we modify stuff though, so it's not like it's not doesn't affect the lookup path. It's just like a little
yeah,
extra overhead when we modify stuff. We
yeah.
need to memcopy
Uh,
potentially a couple thousand pointers.
yeah, that's fine.
And this is
Uh, we're
wrong.
gonna we're gonna batch modify. We'll be modifying a whole lot of stuff, and then at the end of that batch modify, we will update everything, the indexes to be correct once.
Yep.
So we amortize that over the whole batch modify.
Yeah, well, I'm not sure how that exactly would work out with the splitting and whatnot, but we'll figure that out.
Mm.
I think you just end up doing that as soon as you need to split, because then if there's more stuff that would need to have gone into the same node, they'll just get put in after the split. The
Yeah,
split will only happen once per batch anyways. But yeah,
yeah. I thought we could even, if we need to, we can when we'll see when we get to it, but we could even have extra
yeah.
memory that we use temporarily so that we um,
So we've got two things here. We've got the info node, which is a U32, and then we've got the info um, element, which is also a U32. Are you
okay.
happy with these names? Those are like the index
Um,
into these node pointer slice.
yeah,
This is the
yeah.
index
I
into
think
this, and then
yeah, element is within an info node. It's an index in there to the
well,
element.
I think it's across all info nodes. It's the index into the info node segmented array. That's how I was thinking of it at least.
Okay. Yeah. Yeah. Info node is the index into the segmented array. So maybe we can call that info node
This
index.
is the node index. This is the index into the segmented array of all the elements in
Uh,
the segmented array.
okay, okay, yeah, yeah, yeah. But the segmented array has like four nodes. So info node is that index one.
Yep.
Okay, cool. I think we should call that info node index, and then info element is the logical index, as if we didn't have a segmented array,
Yeah.
as if it was just an
Right.
array. Yeah,
I think these names are good. Or
yeah,
do you want to call this info
yeah,
node
yeah.
index? It seems like
We don't have to. Cool. Let's carry on.
I
So
think
info
let's do that.
element,
Cool.
maybe what we should do is call that just logical info index or something like that.
I think that just needs to be common. I think the
Yeah. Or I would actually even call that just index because that's like such a big thing for the iterator. Yeah.
sure of table infos.
Let's say segmented array. Otherwise, we
Oh,
get
sorry.
our
I don't know why I want this.
uh, no worries. It's spaghetti, so I'm actually yeah. It's not necessary even to fix it up now. We just cruise ahead. Whoops, sorry.
Um, Here you don't even need a comment for that one. That's kind of obvious.
Yeah,
Okay, so that's
yeah.
where we're at right now. And then with these two things, can we iterate to the next index? Yes, we just increment it by one. And can we iterate to the next info node? Yeah, we just increment this by one. Once we get to the info node, we've got here the count. Um, Maybe we don't have the count yet. Let's just do the same thing here and then get rid of this one because it's redundant. But let's
Yeah,
just to simplify things, we can have the count here as
yeah.
well. Oh no, we got the count
Cool.
inside the nodes. That's right. I
Yeah,
forgot about this. Cool. So we can't get to the count then. We just dereference this. We put our index in here, dereference it to get the pointer, and then take the count there. So we're actually all good. That's all we need for this is our only iterator state, actually.
yeah.
So now we need a function that takes the output of this, the key index, and returns the info node and index into
To
the
start the
segmented table
iterator at.
infos to start the
Yeah.
iterator.
Yeah, I
Cool.
think that one we should do as a routine just below key index because it makes it nice to unit test outside
Yep,
of having to spin up an iterator.
I agree. Now this is
Cool.
info index, I think is what it is.
Yeah, yeah.
It needs to return the node as well. Um,
It can just return an index and then we can, that makes it easier for testing. Then when we use
well,
it,
we
we'll
need to
plug
return an
that
info node
index.
as well. Or where did we get the info node from then? So we need key. Okay, so yeah, we can just first do info index, and then we'll just do another one for um. This
Cool.
will always be info node first, and then we'll do info index as another thing. Um,
Cool.
then this one's gonna take this will take the key index and return an info node, I believe.
Yeah, we actually want to, instead of key index, we want to use I that we get out of key index on line 6. I is what we want to use here because this is the actual index of the keynote.
Yeah, maybe doing this in several functions is not really helping us here.
Yeah,
Um,
okay. Then
let's
we
just
do,
do it in
let's do
one
it all
function
in
for
one. Yeah, yeah,
now. This is now key node. I think that's what we want to call it. Just key node. Um, or just this is then keys slice. I think is a good name for it. Keys slice. Um,
I like a keynote index, and then we call that keynote because the keynote is the thing, and then it's clear that the
I'm thinking
keynote
about the
is just,
keynodes as the U32s. I
yeah,
feel like that's a little bit nicer.
yeah.
I think it's kind of thinking about it that way because
Okay,
if
okay,
we're doing
cool.
the
Like we
structure
did in
thing,
Eitzinger
because
as
then
well. We did.
yeah, we have here keynote pointer keynote. I think this makes is a nice way to access stuff.
Okay, cool,
Um,
cool, nice. And then we can actually
and
just
then
call that
keys.
keys.
Sure, that works too.
Yeah,
Yeah, there's no
yeah,
reason to call it add the slice keys.
yeah, yeah.
Yep, that's good.
Cool.
Cool.
Yeah, Isaac.
Now
Yeah,
here we've
I
got
keyed it.
this actually becomes just index.
Mm,
Um, this is the logical index we're looking for.
mm,
And it's the same index for the info slice and for the keys slice.
yeah,
Um, now we need to get the info node. Um, this is just equal to we have this cached essentially. We have
yeah,
here keynote keymin info node is what it's called.
yeah. Given
Um,
keynote. I can see us moving this all into our iterator constructor.
probably yeah. Key node. Um, then we've got the info node. Now we just need to find. We now need to jump to the info node and get like the key that matches. Um,
We need to do
that index.
a bit of pre-infusion with our coffee, where we pre-iterate to get the iterator up to speed, and then we that's what we do in the
Exactly.
constructor. Yeah,
Exactly. Um, so now we want to we need to find. We already have the index. Actually,
we've
are
constructed
we
our
now good to
iterator.
go?
Yeah, yeah,
No, actually, I think we actually don't want to store the index here. We rather want to store an index, um, a index relative to the current node we're looking at, because that's what we use to. That's where we're actually going to increment. We're going to increment the index relative to the current node, and then once that
yeah,
hits the node that count, we're going to increment. Then we're going to set it to 0 and increment info node. This is
yeah.
actually should be not index, but like well maybe it should still be called index, but it's not the logical index from the segmented array, but rather the
Mm.
index in internal node.
Or we could just call it, um, Yeah, that's fine. We can come up later and go through the names.
We can improve the names for sure, but I think that's what we should be calculating here, which is
Yeah,
then we're going to say
definitely.
then
Yeah.
I really wish I had a different name though. Um,
Oh,
um,
we'll come back later. Uh,
relative. I'm just gonna call it rel index for now.
yeah,
Equals then level dot key. Well, we now need to go take this info node and put it into info node start index essentially. So info node start index info node. This is now index minus that. This will then give us the relative index inside the index node where the key we found from the binary search is.
yeah,
We might not need any error handling here except to handle like the case where it's out of bounds.
yeah,
Um, because if we just go into here, then our iterator will terminate immediately before returning anything because they'll already see that we're past the key max of the search bound essentially.
yeah.
Um,
The first binary search will find the key node that could have this keyman in. Then we're going to search within those keys to find a to find the logical index.
yeah, we're always iterating on a range. So this is actually what we want to do. If
Mm,
I think we should return early. We return like null from iterator creation if we don't find it here or something like that, because that means there's nothing to iterate. Um, there are no tables. Oh
yeah,
no.
yeah. I don't think we should do that because that bifurcates the code flow. So
Creation,
we
yeah.
just want
Right.
just
Then we
want
got two.
one
Yeah.
two code paths.
We
Just
just
want
want the
one
iterator to
code
return
path.
empty, essentially. Yeah.
Yeah, yeah.
Um, but yeah, I think we
Uh,
just handle that by setting the info node to info node count, essentially. Then to say
yeah,
that the iterator is already out of bounds. But
yeah.
if it doesn't return past the end, then this is exactly what we want because we don't want to find an exact match for this key. We just want to find the smallest key that's larger than this key min, or larger than or equal to this key min. That's where we start
Exactly.
iteration.
Yeah,
And for point lookups, would then you would then like kind of just return the iterator, and you would see on the first iteration that you don't actually yeah, the key's actually not been found because you already get
yeah,
the first iteration is already larger than the key you looked for. Or
yeah,
I guess we would for point lookups you would pass the same key min and key max, so the iterator would just return empty. It would just be an empty iterator, right?
yeah,
Cool.
yeah.
I think the binary search current behavior is actually really good. I think that's exactly what we want. If returning like
Mm.
just the next one greater than
It,
the
it,
key we
it,
searched
it
for.
is, especially if we're using keyman here, then that's it. Yeah,
Yep, it's all
yeah,
perfect.
nice. I'm
Cool.
wondering where we map to relative index into the node. I just want to get my head around that key node, keyman, info node. That's for the key node. Where is the info node that has that keyman somewhere in it?
Yeah,
Now we've got
you're right. I think this is wrong. I think
yeah,
this is because this it doesn't actually give us the exact key info node we're looking for. This just
it
gives us the first one that might have it. Um,
exactly.
so now we need to
Well,
actually do some iteration here to find
it
the rel index.
it
Um,
is it is the first one that does have it. It has it somewhere within it. So the
no,
keyman from this key node is in the info node somewhere.
really?
Yeah, because all
Oh, but
key
this is
nodes
not
are
the keyman we're looking for. This is not the keyman we're looking for. This is the keyman from the
exactly.
index. This is
It's the key node. So the keyman we're looking for is within that key node. Then within that key node, um, we will get the exact logical index on line 2 above, which is correct. That's the actual logical index where we'll find the table info ultimately. If we think of all our
Yep.
table infos as a logical array, that index is
Yep.
perfect. Now, after that, what we're trying to do is we're trying to find the latest info node to start our iterator at. We don't want to start our iterator at 0. We want to find what's the latest info node. And to do that, we go back a little, like we backtrack. So we now take the key node where our key was found. We just take the key min of that key node, and we go and say the key min for this key node, where's the info node that hosts this key min?
Yep.
Um,
And now
that's
we
going
need
to
to
be a
iterate to
little,
find the
exactly. And then we're going
actual
to,
node,
yeah,
which
iterate,
is
and then
well
we'll get
true
up
for
to our,
now. I don't know what.
yeah, yeah,
Uh, yeah, we're
cool.
going to compare actually this key min we're looking for with the first and last. I guess just with the first. Well, I think
We
we
don't,
maybe
we don't,
compare it like the.
we don't want to do a key
Hmm,
comparison. We just need to
we have to
iterate
do a
the.
key comparison.
We don't actually need to. So we've got the logical index. Now we can get the logical index
Oh,
of the
right. I
info
see. Yep.
node, keyman info node,
Cool.
and then we just need to iterate the counts until the two logical indexes match up, and then we can do an assertion that we now have the key matches, but we don't have to do
Yeah,
key comparisons all the way through.
you're right. And so there's car info index equals um in or level info node start index info node,
That's it.
and then so we're going to say while info index is less than index. um Actually we want to say like not equal to index, I think. Then we have to be careful of going past it though. I think we want to assert that they're equal
Less than.
afterwards.
Exactly, yeah. Or that it
Info,
can't be greater than.
but yeah, if we want to find the exact match, I think. um
He okay. Okay. Cool. Yeah. No, definitely. That's good.
Here we're going to increment info node if we so this info index is now the first index. um this actually we want to actually I think we need to use the info node count now at this point. Yeah, we've also got
Exactly.
we've extracted that as well. No, we haven't done that. We can just do info node count, I think.
Hmm.
um
That's it.
Info node pointer info node dot count. um so while info index dot info node pointer dot count is less than index, we increment
Uh,
the info node.
I think that isn't right. It should actually just be while info index is less than the index, and then we do stuff within the loop.
Yeah, but then we're gonna go one past what we want. Is here,
Okay.
um, well, maybe that's fine. Okay, yeah, and I think this is right. I think what we want to do is this. We won't be able to assert that's equal at the end, but let's just trust me for a second. I think it's almost there, I think. Um,
Cool. I trust you
um,
always. That's good.
plus equals. I think we just do this. I think this is our loop, and then at the end we know that we can't add count again. Instead, we can just subtract the index. So var rel index or just const rel index. Now we can do the thing I was trying to do before and do index minus info index to find the relative index inside the node we were wanting to look for.
Okay.
Um, this is right now correct. We should check it though. Um,
Yeah.
we're saying this check is saying is the index we're looking for in this info node. Um, it may be phrased a little bit poorly though. Um,
Because then we know for sure it's
this
not
is this is
this
this is
is
the
a
wrong
this
way
is
to
a
count.
no, it's I like it that way actually. I always like the
Well, I
thing
think at
searching for it at the end because
okay,
we are before the index, so the thing that we're
yeah.
before should be on the left. Uh,
I actually had the sign the comparison the wrong way around. That's what I was saying is the wrong way around. But yeah, we want to say
okay,
like, well,
cool.
this is less than the
Yeah,
index. Then we're gonna
yeah,
we're add count to the current info index. This is like our we can also just call this
yeah,
I perhaps. Maybe that'd be less. Info index is
yeah.
not the best name here.
No, because I corresponds with index. It's like a pre-index. Yeah,
Yeah, it's just like the one that your loop variable. Um,
yeah.
and so I is we start at the start index of the current info node. Then we check is index or well if index is not in this node, then we increment
Jump
I the start of
to
the
the
next
next
node. We
info
could
node.
also just set this instead to I think it'd actually be better cache wise to do this not like this, but to set I equal to this. Um, we could actually do things like we could actually get rid of I and just work on info node and here do no, we already are doing the count thing with in the cache there. Never mind. Just like keep this is correct. We can like improve.
Oh,
We're gonna get rid
yeah,
of well, I don't know because here we're accessing like we can come back when we like optimize stuff, I guess.
yeah,
Because right now
yeah.
we're
This
like
is fine.
accessing a different cache line to do this count variable every time, where we could
Yeah,
be doing this based purely off start index, I think. But that gets things a
yes.
bit trickier. So let's see what to do for that. Um,
Because of the out of bounds check, what we could do is say if the start index of info node plus one is or if the start it is before the index or equal to, then we can increment info node. But the problem there is that we've got the if we're out of bounds, so we can't.
hmm.
Does that make sense? Did I explain it okay?
Yeah. I think you're right. I didn't handle any bounds checking yet. Um,
No, this is another strategy, like going with what you're thinking. So if so, while info node start index, and then we do info node plus one is less than or equal to the index we're looking for, then
yeah.
increment info node.
Oh yeah,
But
that's even better. Yeah.
then we just have to special case the out of bounds at the end because
I think
info
we
node
already
could
didn't
be
have bounds checking though. I think this is
yeah.
a better way to do this though. We just do that. That's what. Yeah. Cool. Of course. Um, and then we just need to like subtract.
That's
Then we
not
go one too far though.
it's it's not quite the same though because
We're going
this
one
is
further than we need to be now. Is the difference?
uh, well, this isn't actually going to help us because the start index of the info node is always going to be, oh, okay, it's going to be less than. Yeah, so what I was thinking is info, when we index into start index, if you just want to write it out just to see, and then we can undo it, but we could do info node plus one less than or equal to index,
Exactly. Yeah.
then we'll be
Yeah.
correct. And we just have to handle the out of bounds access there as a special case.
Exactly. We already need bounds
And
checking.
and we must do less than or equal to the index.
Really?
Oh no, it mustn't be. Uh, it must be. Yeah, no, it must be less than or equal to. So what we're saying here, if the next info node starts at the logical index, we do want to increment our info node. That's why
Yeah.
it's less than or equal to. But maybe this is being too tricky here. But we'll come back to this. And uh,
We'll test it for sure. I think this is better though, because now we don't like access the count variables,
yeah,
which are like not in like all sorts
yeah,
of cache lines. Instead, we just iterate over a contiguous array of U32s, which is what this is, which
yeah,
is much better.
yeah.
Um,
It's quite a cool technique, like where you can, if you are only ever doing batch stuff, you can like pre-compute like little helpers to help your fast case.
yeah, for sure. It's kind of like dynamic programming. It's not exactly the same, but it's the same kind of idea where
Yeah,
you have instead of storing like a count, an array of counts, you store an array of like sums of the previous part of the array,
yeah,
um,
exactly. Yeah, yeah, yeah.
which is basically dynamic programming as far as I understand it. Um,
Okay. I don't even know the introduction to dynamic programming, like what it is.
well, it's just
I just know
like
these
these
these little tricks. Yeah.
like it's the same thing as like use like a hash map to accelerate your Fibonacci function. Like instead of
Yeah.
recomputing every
Okay. Yeah.
you
Yeah.
stick the result in a hash map and then query that instead of running the recursive function.
Okay.
Like the trivial example of dynamic programming, but it comes
Yeah.
up like all the time in like algorithm stuff, like interview
Yeah.
questions, advent of code, that kind of thing.
Yeah. Yeah. Nice.
This is basically dynamic programming, though. Is what we're doing.
Yeah.
Is our caching of this stuff.
Mm.
Anyhow, um, because it makes a lot of like non-constant, like linear time operations constant time, or stuff
Yeah,
like that, or even
exactly.
quadratic time operations constant time.
Yeah.
Um,
Yeah. I like
which is
saying
great.
like pre-compute or pre-calculate because then it's like clear, like
Yeah,
we're doing it in the we basically preparing the way, or we're like
yeah,
it's these are kind of like index structures that but it gets unlocked because of this unique like opportunity where we know that
yeah,
when we insert this tree structure, we don't have to worry about the insert cost. That's what unlocks it.
yeah.
They
Cool. And
even do
then here,
this.
the relative index.
Sorry, Isaac, for like LSM range queries, you can even do this trick for that to speed up range queries across the whole tree. There's one paper where
Yeah.
they pre-compute during compaction, they pre-compute the range query paths. So you actually have all these pointers throughout your tree that so you don't have to do the k-way merge or it just it makes that part way faster for range queries. Which
Interesting.
gets a little bit too complicated for me. Like yeah.
Yeah. I'm wondering, like, with our binary search, how we're gonna make like iterating in the opposite direction just as fast. That seems like it'll be a little bit slower, perhaps, but maybe it's not that bad. I guess it's kind of the same because we find I think it's a little bit different, but it's not dramatically
Yeah.
different. I think it's not
We
the
can
same code
all
path anymore because of how the binary search works. Um,
yeah, yeah. We can maybe like when we've in the reverse way, the iteration just goes in reverse, so that's fine.
yeah,
We just need to check that it's exactly the same and like really solve that one nicely, and not that it's a funky case. But
yeah. So now this has just become our iterator init function. I think it's done too. We've now got the
yeah,
info node and the relative index,
yeah,
and we need to handle balance checking here, um,
yeah.
which means that if we need like a check, well, right now we're no, I think that's kind of we need that before the loop as well though, because this might already be like the last node in the info node. So
We need
um,
it as part of the loop also because as we're updating
yeah, so
info
that's why
node,
we might want to like move our loop condition to be like um, inside the loop body and use while true actually.
yeah, exactly.
Um,
Or just do it in the front as a compound condition, like while info node is, well, info node plus 1 is less than the count. And start index. We just do 2 conditions in the while.
Oh, okay, we could do that. Yeah, that's nice. Nice enough.
Yeah.
Yep.
We can even, I don't know if this, yeah, maybe we must polish this later, but we could even do before the while loop, we can actually just do it and say info node plus equals 1. And then we say while info node is less than node count, info node start index, info node less than equal to index. And then at the end we do a minus, but that's getting too tricky. Like,
That's getting too tricky, yeah.
yeah,
I think this is better like this, actually. Because it makes it
yeah,
clear that you're looking at the next one, really, to know when you're
yeah,
done.
yeah,
Or know if you should commit again. I think this is
yeah.
good like this, I think. I think this is solid now.
Okay.
Handles balance checking properly, because now we'll hit the last info node if we tried to go past the end. And yeah, then we get our relative index. Index minus info node start index info node. It's all good.
Yeah.
Seems right to me. I think then we just return our iterator. I think we should move this to the iterator.init function or the
Cool.
iterator create function.
Definitely. Yeah.
Or actually, it's the whole body here. I'll just copy the body for now. And then iterator, well, this is get tables is what this is.
I
Or
think we should just call
iterator.index.
it just iterate as the function name, like manifest level
Okay.
iterate, because we know that it's got table infos.
Yeah, that makes sense. And this
We're
returns
gonna
an iterator.
iterate the manifest level.
So we'll return an iterator. It's going to take probably the same parameters as the current get tables, though.
Mm.
Um, you agree with that?
Yeah.
We're
Yep.
going to return similar stuff, but it won't be exactly the same. I can delete this now. I've now copied everything out we need out of it. Um,
Yeah.
iterator
Up
is going
top,
to
we
need
can
to
also,
have more field.
if you want, up top we can delete those. There was 1 or 2 routines. Uh, the just where we had key index below info node can go and key index can go if we've copied it. Yeah. Cool.
Iron switch can go down the bottom, maybe.
Yeah.
Get it out of our
Definitely.
way.
Yeah.
So now we've got iterate. We now get our info node and relative index. And then the iterator's got these two things. Well, it's got level. It's got info node and relative index, which are kind of like our iteration variables. Be cool if relative index is the name for the field here. Right now it's just index in our iterator struct, but we can make this like relative index.
Yeah. That's actually the
Just for now,
index inside the info node.
inside. Yeah.
Yeah.
Or yeah. I think that makes it clear that it's different. It could probably maybe
Mm.
be improved on.
Yeah.
But yeah.
Cool.
Just use the full name
Because
here.
yeah, good. Because once we found the logical index, the iterator doesn't actually ever need to store that. It's found the starting
No,
point. Yeah.
exactly. Because then we're just iterating till we get to out of our range based on the key
Yeah.
max.
Yeah.
Well, right now we only support key min. We'd actually have to look up by key max here if our direction was
Yeah.
the other way. Can we make this? Can we just do this for key min right now and get rid of the direction argument for now and have to do add direction? And
Uh,
then come
I,
back and put that in, or do you want to do it right now?
I would say like that interface is good. So then we remember it, we've got it there, and then we can just in here we can add a to do in the source. Like let's add the. Um, we don't have to compile this yet.
Okay. Handle descend.
That's it. Because basically, like this constructor is going to do it a little bit differently, but the actual iterator then on the table nodes, that iteration is going to be it's going to be it's going to be the same whether we go left or right. Uh,
I don't think we can do that with this current structure. Iteration is going to be different depending on whether we go left or right. Just because of the way
after
the math works out.
after the iterator constructor returns, will it still be different?
I'm pretty sure, yeah. Because we need to then subtract instead of add. And we need to
Yeah,
then
yeah, yeah,
do a different check to know when we finish a table. Then we're comparing if we reach 0, and we reset it to the count of the next table.
yeah.
-1.
But exactly. But what I mean is that's all the same except for the sign. It's like if you've got a fixed array and you're going left or you're going right,
Yeah.
it's incrementing
Except
or
for the sign
decrementing.
and the sentinel values you use.
Yeah, yeah. But
And
it's
the
not.
min and max key. We'd have to call this like start and end key then probably. Um,
Yeah, yeah,
oh no.
yeah. Cool. And but all I mean is that I think the constructor part is going to be a little more tricky, but the actual iteration part isn't going to be that bad based on direction.
Construction really more tricky. Um,
Because
we just
our
like pass in key max here, right? And then we find, I guess we get something on the other end. That's the problem. We now get like past the key max potentially, and we need to like
hmm,
iterate backwards to find
that's
the first thing less than the key max.
Yeah, that's what I
Yeah,
mean. It will have to do a
that's what
little
you're
bit
talking about. Yeah. Okay.
extra work here, but the actual the like the data plane of the iterator, the main part, once the constructor's done, that's going to be the same complexity left or right. That's uh,
Yeah. Okay. I see what you mean there. It's just a little bit. There will be different code paths in there, but it'll be the same basic algorithm.
yeah,
Um, Here we actually
yeah,
need to do extra work in the case of descending a direction.
yeah,
Okay, we should actually do an assert here, just to make sure we don't do something stupid. Um,
yeah. Good. Oh, and we can also do if the key is found. If we know that we have the logical index and I and logical index are the same, then we can do an assert that the keys match in the info node. Keyman matches the info node
the
keyman.
key is found. What?
If we have at some point in the constructor, we're going to know if the key actually doesn't exist in a table at all.
We're not going to know that actually. We'll only know that if we end up um,
Out
off
of
the
bounds.
deep end of the table.
Okay, yeah.
Otherwise, we're just going to get the index, um, the first index that's greater than the key min. That we're going to get.
Okay, yeah. Okay, so what we could assert is if we do have some kind of table info that matches the range, because by now, once we get relative index, we should know that we're at the start of the range. We could then like assert that the key min of the table info is actually before or equal to our key min here. Just
Okay.
before the constructor returns, we can assert
Sure. Like
on
right
key
here, you
min.
mean?
Yeah,
So key
unless we had an early
min.
return.
Sorry.
Sorry, yeah, unless we had an early return, because we know we definitely don't have a table info that intersects.
I think
But if we do,
we should not we should handle that by just having the iterator return null right away rather than doing an early return. Because then you only have one code path in the call site.
yeah, yeah. So we don't. I'm confusing. We don't want to do an early return exactly for the reason you say. We don't want to bifurcate the code, just one code path. But I'm just saying this assert will be conditional on if we know we actually have a table info.
I'm not seeing what you mean. I'll show you the
Okay,
assert better,
okay.
guys.
No, go for it.
We need to now go into info or level info node pointer. A node, and then we need to here actually go then into key min. I think that's what we called it.
Yeah,
Yeah, just key min
yeah.
and then relative index. This is now the key we were targeting, and we want to make sure that what this relative index key, or this, we can actually have one more thing here. Let me just say equals
It can be greater than or equal to, so it must not be
yeah.
less than. Not less than. Yeah.
That right? Is it the right direction? We say our key min must not be less than. Yeah, that will happen if we don't find the key min. This is the wrong way around currently now. It should be not equal to greater than.
Uh,
Yeah.
you see that the assert is wrong if we know for sure there's no table info, then we can't do the assert.
If we, sorry, what? If we know for sure there's no table info.
So if the very first call to the iterator, once the constructor returns the iterator, then on the iterator we called it.next. If the very first call is going to return null, then we can't do this assert at all. But otherwise,
Oh, I see.
generally, if we do have stuff, then we want to say it's not equal to less than. What we're saying is the key min we're looking for has to be greater than or equal to the first table info's key min in the iterator. So it's actually less than, so not equal to less than there. That is,
Okay, so this is not. We're not asserting that the key was found. Well,
yeah, yeah.
it still seems wrong though. Like, what's this assert even checking for us then?
It's it's checking that the key min is not less than the earliest key min that we have found for the info, for the first table info, because we don't expect that. Our binary search will return the the first table info.
That can happen though. If the key min is just lower than the lowest key in the LSM tree. Like this key just doesn't exist in the whole tree, and it
Yeah,
happens to
but
be like
then
0.
exactly.
Then this
Okay,
assert would
okay.
fail.
But then this iterator should also not return anything. That's
Yeah, but we
okay.
can't
So
really use this.
actually, yeah, in our constructor, maybe we can add a to do. We've got to handle the case where we outside the tree on either side. We've so far we've thought of
Okay.
overflows being outside the tree on the max side, and we've just discovered that we can be outside the tree on the min side also. And in both
Yeah,
cases, the
but
iterator when you do the first next call, it's going to return null because there's nothing.
yeah, we don't need it. If we didn't have this assert, it'd all be fine for the min side. I'm pretty sure. Like,
Yeah, yeah.
we just
Okay.
can't assert here because we we are assuming that the key might not actually be in our tree.
Yeah. Okay. You think it's time for lunch?
Um, yeah, just about. Let's see. How much time do we have left? I've got to go at 2. We've already got it's half past 12, so we've got an hour and a half left in total.
Yeah.
Do you want to do a quick lunch now and then come back for a bit after that?
Yeah. Yeah. Shall we come back on the hour, like in 30 minutes, and then we
Sure.
carry on?
Do a
Or
half hour lunch and come back in the hour.
yeah, but if Isaac, if you think maybe we need a 45-minute break because my head feels pretty. Like,
Okay.
how
Do like
you
15,
feeling?
15 quarter past then, and then do another
Yeah,
45 minutes, and then call it a day.
yeah. Call it a
Cool.
year. Uh,
Call it a year. Yeah.
yeah.
All
Awesome.
right.
Catch you
Perfect.
just now.
Here we're not quite done with this stuff yet. Then we'll do the actual iterator, I guess, afterwards, and then maybe we'll
Yeah,
talk about the direction stuff. Cool.
yeah. Shall we, after lunch, do you actually want to, because we've actually sketched this all out now, so do you want to tighten it up after lunch? And we actually go through
Well,
slower.
we haven't done the iterator yet, and we haven't done the creation yet.
Yeah.
Or version.
Okay, so shall we just keep sprinting for all that stuff, and then next
I
year we'll
think we
come
might
back
want
and
to get that
tighten it.
stuff also kind of sketched out, especially the
Yeah,
insertion will get tricky.
yeah,
Or at least like export it more.
yeah.
Yeah.
Okay, catch you just now then.
All right.
Awesome.
See you then.
Hey, Isaac.
Ready to go?
Yeah, welcome back.
Cool. All right. Screen share should be going now.
Yep.
All right. Yep. All right. Ready to get back into it then.
Yeah, awesome.
Cool. So we just finished our iterate function. Or well, this function just creates the iterator. It doesn't actually do the iteration. We still need to do that part. So we do that next. Just implement the next function of the iterator.
Yeah, yeah,
Um,
yeah. That I think that would be great to do.
cool. We also need to update. These are now. Well, you don't need to have the dot comment there because it's part of the iterate API kind of.
Mm.
We don't change our. Hmm. Yeah. Be kind of separate. I feel like. Well, never mind. I don't know. Snapshot max. Well, snapshot. How do we compare it to the timestamp? So we want to like compare. This must be like between the two timestamps then, right? Or the timestamps. We've got here timestamp created and timestamp deleted,
Yeah,
and so we want to make sure that um timestamp deleted comes um before our snapshot. If timestamp deleted, wait, how's this relate to these two timestamps there again? Just trying
yeah.
to think through how we did the filtering here.
Cool. So
Um,
the snapshot must be after greater than equal to created, and it must be
yeah,
less than deleted if deleted is there.
if deleted is there,
Yeah.
um, and we use like a null value as 0 to indicate that deleted is not there. Is that what we do then?
Yeah, yeah. I guess this is all just in memory, so we don't need to worry. We could then use a sentinel there.
Or deleted could be then actually max int then. That actually would be
Yeah,
and we wouldn't even need to check for it. It just has never been deleted yet.
that's better. Yeah,
Cool. And then we just say if the snapshot we would use like less than or equal to here then because our snapshot yeah I think that's what we well
it's
there should be
it's
like
got
max int minus one I feel like I don't know um
it's got to be less than deleted because
yeah
if the if it's equal to the timestamp and when it was deleted, then um,
is that even possible that it could be equal um
I don't think so. But we'll see how we generate these. I guess okay. So the first thing is we'll have like a counter that we increment each time we create a new table. That's what this timestamp means. It's just
yeah
the table number, and then when someone creates a snapshot, we will issue them. Maybe we want to bump the number then as well, or maybe we don't want to bump the number because otherwise they could issue a snapshot, they could acquire a snapshot, release it, acquire, release, and then it's just bumping our number. But it's a
yeah
U64, it's a U64, so even if they did that, they're never gonna get uh,
I think it's fine to not bump it though. I think
yeah,
we just need to handle equals here properly which I think
yeah,
is probably good
yeah.
um
So it would be greater than equal to created and less than deleted.
unless then deleted and so if we make deleted u64 max then we can say if you want your snapshot if we here to indicate there's no snapshot you want actually minus one here then I think is that right
Yeah,
which is fine we can have like add a constant for this in our LSM file um or we can just make this parameter optional
yeah,
and then here internally to this pass minus one or maxing it minus one
yeah. We're gonna do. Are you thinking of a case where you can see everything, the latest activity,
I'm thinking of when there's no snapshot
Yeah,
in the query.
yeah. Then, and the table hasn't been deleted.
Yep,
If the table isn't deleted, its deleted will be set to max int.
right. But then to use the same code path, we want to actually be able to compare with less than, not less than or equal to.
Okay, that's it. Now I understand the -1. Cool.
Cool. So we should have a comment here. Um, if not, get deleted.
Yeah,
Cool. This failure is yet to be in parentheses. They may never be deleted. We never know.
yeah,
Um,
yeah. Let's do a full stop also then at the end of that.
sure. All right. Now we need a next function here. This will
Yep.
just take an iterator. Iterator returns an optional. What's return? Like an optional table info.
Yeah,
Um, we'll just reconstruct this table info struct from the various fields in our structive arrays here.
yeah.
Is fine. Um, cool. So here, I think what we do is first we check if we're out of bounds. If we're out of bounds, return null. Otherwise, return the thing at the current index, and then increment the index.
Yeah,
Does that sound like a good control flow? Or I guess like set a variable to the thing at the current index, then
yeah,
increment the index, then return that thing.
yeah.
So first bounds check. This bounds check, we're gonna first check the node if the node's out of bounds. Well, no, first we check if the index is out of bounds for the node. We should do this actually at the end, I think. I think we should just
Mm.
check if the node's out of bounds here. And we'll do the index out of bounds for the node check when we increment the index, and then reset it to 0, and increment the
Okay,
node if we necessary.
okay.
That comes in the increment. And so here we just check if the node's out of bounds. So if it.info node is greater than we need level here. Um,
Oh, we've got level already. We've got it
no,
further
we
down.
do. It's just in the
Yeah,
wrong place.
yeah.
Um, level dot able node count. What's it called? It's info node count. That's right.
Mm.
Info node count is greater than or equal to
Yeah.
um,
Return null.
return null. That's the first check. That's easy. Now we're gonna construct the table info that we're currently pointing at. Um, info equals table info. We're just gonna get all the things out of the various arrays.
Yeah.
Um, I'm gonna copy this stuff so I can just like, or not
I'm
this.
I'm wondering,
Um,
Isaac, over here, I
yeah,
think maybe we want to change it because we're doing our within our info node, we don't actually leverage the structive arrays for that, uh, aside from uh, padding.
yeah. We
Yeah,
don't ever. Yeah, it's really just helping us with padding, but maybe that's not an issue.
exactly. And I
Well,
actually think we don't
I
want
think
to.
it does help with padding. It is necessary for padding, I think, because otherwise, with
Yeah.
larger key sizes, you're going to end up with padding in every table info.
Okay.
Maybe it's fine though, but
It's almost okay because I think what will be better is if we return a pointer. We don't want to copy because otherwise, if we're doing every level in a tree like six times, and we're going to be copying quite a lot of data, like 96 bytes times 6, just to do a lookup.
okay.
Yeah,
Yeah, that's
every
fair.
What do you think?
I think you're right that we should maybe just store them in.
Mm,
How much padding do we have in one of these? We've got this is a line 16. This is then potentially also a line 16. But there'll be no padding after this.
yeah,
Um, in the case of this is a line 16, we'll have another one of those, still no padding. We'll have 8 bytes of padding per table info in the case of a 32 byte key.
yeah,
The key is 16 bytes. Um, it's the same thing. The key is 8 bytes. It's always gonna be 8 bytes of padding per table
yeah.
info.
That's
And
fine.
so, okay,
Right.
so
I
we just
think,
get rid of the structure of arrays here,
yeah,
and use instead of this calculation, we use size of table info.
yeah,
Um,
nice. I think here's where we do want padding because it's worth it for the lookup speed. Also because if we constructing the table info, we're not just doing the copy, but we're doing the cache misses for each of the fields because
that's
they're
true as well.
not
Yeah,
not
we're
contiguous.
not
Yeah,
actually iterating by field there. We're just iterating by the whole thing at once.
yeah,
At one point, I thought we were going to be iterating over the keys in this thing, but we aren't actually doing that. We know the index,
yeah,
and yeah.
yeah.
So info, just a capacity table info now. And I guess we
Sweet.
get the count. It's just going to be there's just going to be some padding here.
Yeah.
Our other stuff this takes us into account for our allocation requirements,
Mm.
and so we should be all right there.
What do you think of Keynote and InfoNode? We actually, okay, well, for InfoNode, it could make sense. InfoNode, we make info actually a slice. That way we don't need count anymore. We just get it more ergonomically as part of the slice. And
Well, um, that that doesn't really work with how we got the setup right now.
mm,
Um, right now, this is the memory of our block of memory. Like we get a chunk of memory from the pool allocator, right?
yeah,
And we bitcast it to this type. Um, if we replace this field with slices, which is what I think you just suggested,
mm,
then you've got here then a pointer to a different block of memory. Um, and we don't want to store point slices here instead of pointers, so that would take a lot more memory.
uh,
Slices are twice as big as
yeah,
pointers.
okay.
Um, we could store the counts outside of the info nodes inside. Actually, I'm thinking we might be able to get rid of the counts too, anyways, because of we may be able to just base it off of
Yeah,
the start index stuff.
mm,
We subtract this one or the next one from this one to find the count. I'm pretty sure.
yeah,
And then we need to like store an extra one for the last one. Do you want to like move to the same pattern we have here for now and have like the counts currently stored here,
yeah,
and we're gonna actually get rid of that with fancier code.
yep,
Um, eventually, and get rid of the count from the info node thing.
yeah. I think that's cool.
Uh,
Okay, I'm with you. I understand. And we couldn't, yeah, we can't really. It's yeah,
we can
I'm
just
with,
make
yeah,
these type tests for arrays though instead of having them be extra constructs to be the
mm,
same memory layout.
yeah. It's basically just down to one field now.
Yeah, exactly. I think they should just be array type defs.
Yeah,
Then we don't need to go do keynote.key
mm,
um, index. It just be keynote index.
mm,
Um, info node counts, info nodes max. This can be then key or const node, or we just, or do we want to just like put that in here and do like have a key node capacity and info node capacity things like key
as constants. Yeah, I think
node
that's better doing all our constants in one place.
is this. It is a bit simpler, I guess.
Mm,
This is key node capacity and oops table info. This can go like after the info node max. We do info node capacity. And then here, we just gotten rid of keynode. Is now instead of a pointer to keynode is a pointer to an array of keynode capacity key. And here pointer to an array of info node capacity table info.
Nice.
Now we got all our data in these fields. There's no other structs now. This capacity function needs to be that's old outdated stuff now. We've gotten rid of the size and everything, so we can just delete this as well.
Sweet.
Cool.
And are we going to get rid of the optional type on keynote pointer, info node pointer? Or what? We decided that it's worth having with current sig. Info node count.
For safety.
Yeah.
We don't actually use that data. It's just there for safety checks.
Yeah.
Make sure we don't write bugs.
Okay.
Or to make sure our bugs cause crashes instead of undefined behavior.
Yeah.
That's really why it's there.
Yeah. Yeah. Downgrading correctness into liveness. Yeah.
Exactly. So now we're gonna here turn an optional pointer to table info. Because info equals the address of it.level that info node pointer. Well, here actually I think we want to do first do like infos equals this it.info node slice to the level info node count it.info node. This is too long, but we'll have to figure out a way around that.
Cool. On when we do it, yeah, that's it. I've had an idea too. I think in this context it makes sense to say keys and tables, and instead of saying info node, call it a table node. And it is all metadata already, so focusing on the info part, we put that in the type. But then we've got a nice plural. We've got keys and tables. And tables are kind of what this is about, the whole thing, tracking all the table.
All right.
Yeah.
Cool. That's done.
Sweet.
Let me see if I still have any infos lying around. I do have some infos lying around. Let's fix these ones too. That should be all the infos now. All the infos are gone.
Cool. And we could even we've got min tables per table node. We could actually just say they're min tables per node.
Min tables per table node, or min.
Yeah, it's actually just min keys per node.
We got rid of this. This is now. We need to do these capacity things first, kind of. Like logically, they don't need to do them first because they isn't order dependent, but logically they come first.
Exactly.
I'm gonna flip the order there.
That's
good. Capacity, the min tables per node. Yeah. Well.
That's it.
Right. And here, same thing. Keynode capacity. Keynodes max. Here, keynode capacity divided by 2. All right, that looks good now. All right, now this needs to be simplified somehow. Now it's just gotten longer because of that rename. Info is 1 character shorter than table.
Yeah.
Okay. Need that table node. So this is the table node pointer. maybe just do pointer equals and then here do pointer slice to the length, and we got tables. And now we can clean up the code later if you like, but that works for
Okay.
now. It's short enough of the lines.
Cool.
We now need to say const table info or result. We can just call it table info maybe. Well, we need to check here if relative index is out of bounds. No, we just do that when we increment it. That's right. Okay, so it's dot relative index with bounds checking now because we've sliced it to the right length. And now we're going to do the increment and then do the bounds checking. So then we can do it dot relative index plus equals 1, just unambiguously, and then we're going to check if it's out of bounds. So if it dot relative index. See, what we really should be doing is putting this count out because we're going to need to reuse this one, not the pointer.
Yeah.
Const count, and then the pointer we can maybe just put back in line then.
Yeah.
Cool. That's better. Is if this is greater than or equal to count, then relative index equals 0. Oh, well, here's the stuff that changes depending on direction. To do or assert. It table node plus equals 1, and then table node bounds check happens here in the next iteration.
Yeah.
You happy with this? Then we just return it table info.
Yeah, that looks great.
Maybe like get rid of the space there. Whoops, what have I done?
Yeah. Cool. I had an idea. We could do like in this iterator context, instead of having table node and relative index, we could just have iterator dot node and index because this is only going through the table nodes. What do you think?
Well, its index needs to be clear as relative to the node.
Yeah.
Maybe that's fine.
Then we could say node index.
That sounds like the index of the. That sounds like it to be the same thing as node. I think node and index
Okay.
is better than node index.
Yeah.
Just node
Yeah.
and index.
Node and
We
index.
just
Cool.
document that is the index inside the table node.
Yeah. Cool.
The current.
Table node. Cool. And we can put a full stop there at the end.
Sure.
It'll make this a bit lighter to read. You also happy with that?
Yep.
Yeah.
And then
We've got some relative indexes.
Whoops. Dot index. That is a bit more readable.
Yeah.
It's less text.
We could do the increments in that in a defer branch. Although is that too tricky? We rather want to just cache the
I
table
don't really
info.
like it.
Okay.
I'd rather just store the pointer here and return it.
Okay.
I think introducing, yeah, I don't know. I'm not really a fan of that.
Okay.
It is kind of nice because you don't like have the temporary, but this is actually completely free as far as the compiler is concerned.
Yeah.
Like the compiler doesn't have any trouble optimizing this properly.
Yeah. Yeah. I wasn't worried about that. I was just thinking it's nice to have the it doesn't matter. This is fine.
Cool. I think just keeping the control flow as simple as possible and just like top to bottom as possible
is
is
better.
good for
Yeah,
readability.
I agree.
You only use defer when you then have to do something at multiple return locations.
Yeah,
Um,
yeah, exactly. It worked out once well, like in our ring buffer or somewhere where we did it,
yeah.
because it was so
Then
simple.
like then because what we did there was I had code that just like redid some calculation instead of introducing a temporary,
Yeah,
reversed the calculation instead of implementing the temporary, and then the defer was better than that. But the
yeah,
real solution was just caching the result and then returning that result, which I
yeah,
think was what we have now.
yeah.
Um, um, that was what I'm not sure which one that was anymore.
That
It was
it was
this one, I
still,
think.
no, it's a bit further down in our iterator next.
But we still have it here.
Yeah,
Yeah.
we
It's where
decided.
we used to have it up here in Papa's and put in Papa's push as well, I think.
Yeah,
But
yeah.
now we just set the or cache the result and then advance the head, then return the result
Mm,
instead of whatever we were doing before with the defer, I believe.
mm. Cool.
Anyhow, it's not terrible here. It's only like a 3-line function, but I think just in general it makes more sense to avoid defer if you
Yeah,
don't have multiple return locations. You want to do the same thing at all of them.
yeah,
Um, I figure it should really be used purely for resource management, not really for control flow.
yeah.
Um,
Control flow you want top to bottom. Yeah.
yeah,
I kind of think of it as like resource management for the iterator. It's the thing you always want to do at the end of the function uh, when you set it up, and then you're free to just return. Yeah. But I'm happy. I'm totally happy with this. This is fine.
okay,
Yeah.
cool.
Uh, and then count. Okay, we've got it like that. Tables.
Or table's length, maybe? I don't know what to call it. We could also just use tables.length here, actually,
Yeah.
if we wanted to.
What were we using before, Isaac? Count.
Count.
Okay. Yeah.
Maybe a bit more idiomatic, and this could be then actually table's length
Yeah.
about that.
That's cool.
Cool, this all looks good to me.
Yeah.
So that's only for one direction. Do you want to just do the other direction now as well? Because it's pretty easy, actually. We only switch inside this little thing here. Oh, actually, we haven't
I
done the
think.
key max, key end. We only handled going past the end. We haven't actually done the key min, key max termination
Mm,
condition.
mm,
So we do need compare keys as we're iterating.
yeah. Okay. Yeah. Let's go for that then.
And so I think we do that here after we've gotten the table info. Um, I think what we do is we check if the keys if this new table info that we're about to return is out of range. If it is out of range, then we're going to set it.node to it.level table count null. Does that sound good?
Yeah. We've also got to increment. Maybe we want to do that control flow after we've done the increment stuff,
I
or not.
don't
No,
think
we
it
don't want to.
matters.
It's just that we want to, each time next is called, oh, it's going to be the same either way. Cool.
Yeah, I think we want to do it here really. So we don't need to increment before we do this, so it makes
Yeah.
a lot more sense to do it this way, I think. So
Mm.
if um well, we need to have two checks here, like switch on the direction, I guess. Let's just keep the ascending assumption for now, though. This means that if um, the key is greater than the key max or iteration, if compare keys table info dot
Keyman.
key min Yeah, because we want to make sure if the table has got no overlap with the key range we're iterating on. And so it could be on the last iteration that we returned a table where the key max um, was less than our key max
Mm.
already. Now we're comparing the key max to the key min of the new table that we're not going to return. Okay, cool. Table info dot key
Kim.
min and it dot key max. And then we're going to say, is the table info key min greater than greater than, is key max inclusive or exclusive? I think it's inclusive, right?
Inclusive, yeah.
So we want to say if it's greater than, then we're going to return null, but before we return null, we set it dot node equals to it dot level dot table node count.
Okay, nice. Yeah, that's a good way to do it. We also need to compare against when we go through when we do our binary search on keys, we comparing against table info key min all the way down. So I feel like in our iterator, we want to also compare against table info key max. I'm or just to understand how it relates, like we think through that.
Okay, I'm not sure I follow exactly what you mean yet.
So
Um,
uh, we've got to this first table info only on key min, but we could also look at the table info's key max to see if it fits in with this. We might be able to return null.
that would be then, so I think it depends on the iteration direction, first of all.
Mm,
We'll need the key maxes when we're iterating in the other direction. That's what we'll check. We'll check if the key max is less than our key min. We'll kind of
yeah,
like flip this condition around. So we'll compare table info.key max and it.key min when we're iterating the other way. Um,
okay.
that makes sense?
Yeah. I'm kind of just what it would be nice to sketch out all the relations. Like if we enumerate all the keys, we've got table info key min, table info key max, it key min,
Yep.
it key max. And I'm wondering and then we've got ascending and descending. So for ascending, we've got a few combinations of keys. And I thought it would be good to think through all the combinations just for ascending and see that we get it right. Like just to check what we expect to be the case.
Okay. Um, yeah, we can assert that if this is returned, if we have not hit this check, we could then compare the key max of the table with our um, our key max. Well,
So
we
like
want to assert that we want to assert that the table overlaps our key
exactly,
range.
exactly.
And to do that, we can actually have to look at the key min of the table and our key max again. I mean, there's no other way to do this. There's no other way to put this assert, I don't think.
Couldn't we do? I'm just asking questions, like just uh,
Okay.
to sketch it out. If we do, we not also need to check it key min versus table info key max?
Yeah, well, we're assuming that's the case. We can assert that in every iteration for sure. We never
Yeah,
need to check that because that's what our start condition was. That's like what our initialization function set us up with.
yeah.
Um, it set us up with the first table for which that guarantee is true.
Okay.
Um,
So we could, if we
and
can
so,
assert it, then that would be good.
oh, you're right. We don't actually know that for sure though, because we tried to assert it here, right? But then we
Yeah,
realized that this thing can actually return something past the end of that.
yeah.
So I think you're right that we need to actually try that here.
Just to try and, I didn't even think much about it, but just to enumerate all the possible states and then like write out the branches and then check that we handle them, whether it's with an early return or an assert or nothing, or just to work it through in our
Sure, that makes
thinking.
sense.
Yeah.
So I think you're right. We have to actually return null, um, or I'm not sure how this works out. There's the chance that like the keyman was found. Like, yeah, so like this is already good here. This is the right end condition because there's a chance that the keyman found during initialization is already greater than our key max, and that's what this case handles. This is actually the same thing we tried to assert down below, I believe, but we
Okay.
realized we couldn't assert it because we need to check it here. This is always the end condition for um, the iteration in this direction. We can then just assert or regardless that the other thing is true,
Cool.
comparing the table info.keymax with our keymin.
Great.
Well, it's not great. I can't do that. With that keymin, I want. Sometimes I want operator overloading for these kinds of things, but I know that there's too people will just misuse it. And it'll suck, so I don't actually want it. We
No,
want to insert
Isaac.
that.
No, no operating overload.
No. I know that it's like what's it called? Um, so it's like
It's
there's no way
called
to have it
it's
without it being misused.
it's called magic programming.
It's called
Yeah,
C++ complexity.
yeah,
At least for low level languages. For high level languages, whatever, abstract all you want. Um,
yeah, yeah.
table info.keymax it.keymin. And so now we've got to go. So this we know we want to assert that the keymax is greater than our keymin. That's basically all it is. Um,
It can also be equal to.
or equal, yep. So it's not equal to less than.
Yeah.
And this is all. Let's just do the directions now while we're thinking about it.
Yeah, yeah.
We don't need the special code here, like the tricky code here. This is just pretty much just reversing the cases.
Mm,
The tricky code comes in the initialization part where we've got to then like do some extra checks to find the start because
exactly.
of our binary searches properties.
Yeah,
So we could actually do a second binary search implementation that has the opposite characteristics. Maybe that's the way to go.
I think so. And we could, you see, then when we construct the iterator, we can actually have a pointer to the binary search function we use. So we're not even branching in the next.
I think the branch is cheaper than a virtual call.
Okay, okay, cool, cool. Yeah.
Okay.
So for this direction stuff, maybe what we should do is like exhaustive switch on direction like this, and then within each
Yep.
branch, we just want to write it out in full, write out all the comparison cases, and have
Well,
blocks
there's always
with
these two. It's always the same
okay,
two.
okay,
Now we're assuming the opposite, that the key min.
okay.
Well,
No, that's fine.
actually, I think so.
I think
I
our
think we
search
switched.
has
We actually switched.
got a little bug also.
Which one?
Our first one for ascending.
Yep.
So we're saying here that key max can't be
Saying
less.
it's greater than or equal to our key min.
Okay, and our binary search is going to return the smallest thing that's bigger than or equal to what we're looking for.
Yep.
So that is correct. Yeah. And if it's equal to, it's fine. Uh,
Yeah. And binary search works in the key min of the table info though, which is also correct. And
yeah.
here we actually assert on key max.
Mm,
Maybe we should actually be starting on key min. Maybe this should be table info key min actually.
mm.
think that's actually correct. We don't actually look at TableInfo key max when we're ascending.
Yeah, that's another way to think about it.
You look at yeah. And then here we're gonna do, yeah, I think this is actually the tighter assert, because this is what our binary search looks at,
Mm,
is the TableInfo key min.
yeah,
It finds in the first table where this key min is greater than or equal to our key min.
yeah.
Yeah,
Speaking,
this is better.
awesome. Speaking of tighter asserts, shall we call it a year? Like with the assert is the last thing we've done. I, I've
Should we
got
finish this
to.
branch first,
Let's
or you
do
gotta
that.
go right now?
No, no, we're
I
good.
think
Let's
this one's
let's
is
let's finish the
just
branch.
well before we like leave code that's wrong in the
Right.
code base.
Exactly. Yeah.
um,
I'm gonna
it's this thing.
I'm I'm gonna go catch Proddy just now for the IO on the hour.
Oh, cool.
So I wanted to leave us a minute or two just to end off, Um,
All right, and then we got here. I'm just flipping around the logic from up above. I think that's the right way to do it.
yeah. Yeah, that's very nice that it's aligned like that.
Yeah, so cable info key max um, is then less than our key min. Yeah, exactly. That's perfect. Cool. That's all right. And now, actually, here we need to add a different check here as well. We need to check if it's greater than 0. Um, or maybe if we need a sentinel there. I'm not sure. This is to do. We have an assert here for still.
Mm.
This is our to do assert.
Direction is ascending.
Well, just do this to make sure it's clear that's grouped with this condition here, not just for the
Yeah.
whole function. And then we have the same thing here. And then these ones are actually, this is all good now. This needs to be int n equals 0.
Mm.
Um, and then I'm cool to call it a year now.
Let's call it a
Um,
year. Yeah, awesome. Hey, so since March, like we've been, yeah, working, and it feels like it was March last year that we started working together on this stuff.
yeah, it
Yeah,
hasn't even been a year yet, actually, since I joined the project.
no,
Like
no.
3/4 of a year, roughly.
Yeah, but it feels like, I don't know how you feel, like it feels like a year or
Yeah,
two or a long time. Yeah. But
we've come a long way since then, for sure.
yeah. Yeah, no, awesome, and wishing you like a safe flight and happy holiday, and
Thank you.
catch you in Jan.
Yeah, and see you in January. Have a good holidays.
Yeah, yeah, great. Yeah, and everybody else, awesome holidays. Over to you to sign us
Yep,
off,
and
Isaac.
catch you.
Yeah.
Oh yeah. Um, Tiger Bill sessions, Thursday the 16th of December, session 5, signing off.